Okay, morning everyone. At least the flow of people trickling into the room is dying down, so we can go ahead and get started. I had the slide up for a little while with some instructions on how to go and get signed up. Can you put your hand up if you've already started following through those instructions for signing up? Just so I can get a rough idea. Okay, so I'll leave this here for a minute more, but what I'm going to do is talk through, I've got a few slides basically to kick off the tutorial. In that time, we have some like cloud VM resources for you to use to like follow along with the material. Everything's kind of set up through this NVIDIA course that you can find on learn.nvidia.com. Use the code at the bottom to go and register. You get access to the course. That will also give you access to a machine that can run the material. Work through all of that together. Now we should have some like pre-warmed hardware ready for people to log into and get access to, but equally, like if we run out of that, or more people come in than we like have pre-allocated for, then machines will start to boot like cloud VMs and stuff, and that might take a minute. So I encourage you all to go and start clicking on these things now and get to the point where you can log in and click start on the instance while I'm kind of waffling through the first section of this tutorial. Things can join. So I'll give you a minute to just go take a picture of this. We'll take in the instructions for a minute, and then I'll move on to the next slide. Go to the browser. Yeah, please make sure you use Chrome or Firefox. Some people have tried using not those things so far this morning and have basically the challenges. So if you can use Chrome or Firefox, that is preferred. But yeah, the main thing is to go and sign up on the learn.nvidia.com website, create an account on there, and then put in that code at the bottom of your lab, NV24 code. You should get access to this course, this Intro to GPU Python program course. Okay, people seem to be clicking and doing things. You've had a second for a photo, so I'm going to move on. I will put this slide back up again a bit later if anybody needs more help getting set up with that. But just to move on to some logistical things, this is like a double tutorial session, so we've got kind of 3 hours of talk time. There's a break in the middle. Some of the other rooms have got kind of 2 different tutorials going on. There's a break at 10:30 for 20 minutes. So we'll follow that as well. I assume there'll be coffee and things. So we'll go for 90 minutes, go and have a break for 20, and then we'll come back and carry on with the back half of the material. Other things is, so my name is Jacob Tomlinson. I'm a software engineer at NVIDIA. I work on a project called Rapids, which is like an open source GPU Python suite of projects. Some of my colleagues are here who are also going to be helping out with the tutorial. So folks, can you wave if you're going to be here? I'm going to stand up here and I'm going to run through the tutorial material and go through all the notebooks kind of for you all. And my colleagues will be able to kind of run around the room. So if you have any questions, just put your hand up so we can come over to you. If it's a question that we think would like benefit the whole group, then there's a mic floating around as well, so we can ask it kind of in a broader group and kind of dive into whatever that question is. Like all of this stuff that I've got prepared, there's like a path that we're going to wind through a whole bunch of notebooks and things, but I want to be led by you all, basically. Like if you have questions, if there's areas that you want to dig more into, I'm really keen for folks to ask questions, and then we can kind of go off-road and answer different things and kind of do what is most useful for you in learning about this topic. So, as I mentioned, we work in a group called Rapids, which is this open source community focused on Python, data science, and GPUs. You can go find us on GitHub. We've got a whole bunch of projects there. Some of these projects are designed to mimic the APIs of existing libraries or to work as kind of plugins for existing libraries. We want to try and come in and kind of support existing projects and support existing communities by just adding GPU acceleration in places that people already want to be. So can we take the code that you're already writing, the things you're already building, and add GPU acceleration in the places that you'll get some benefit and that you get some value from having that added performance. So like one project that I want to highlight that we've been talking about a lot the kind of last year or so is this project called CuDF.pandas. So put your hands up here if you use pandas. Good, okay. There's a good chunk of the room, right? Pandas is a Python library. It runs on the CPU to do various operations. We have this library in Rapids called cuDF, which is kind of a re-implementation of pandas for the GPU. It follows the same API. But we also have this great extension, this plugin, which you can load before you load your pandas code. and it will kind of intercept your pandas calls. It actually intercepts your import of pandas. And whenever there's an opportunity to accelerate your code, it will prefer to use the cuDF implementation, the GPU implementation, to do things like read CSV and group bys and joins and whatever else it is. The cuDF and pandas library will kind of intercept that. So the goal here is that you can just take your existing code, you can load the plugin, use the GPU, and get some benefit out of the box. You don't have to rewrite your code, you don't have to do anything, you can just use the extension. There's a few different ways to use the extension. This slide shows the kind of IPython Jupyter kind of way of doing it with a little magic where you load the extension. You can also just, if you have a script that you run on the command line, if you would do Python space my script, you can do Python -m cuDF pandas my script. And you load this module that then executes and it does the same injection basically. And you can also write it in Python. You can import the loader from the library. So if you go to the documentation page at the bottom, you can kind of find out more about exactly how to use this. And this is kind of a core theme throughout Rapids, right? We want to be able to take existing code, the blue lines, give you some plugin, some library, some extension, or contribute to some existing open source project and add GPU acceleration so that your code can then become the green line and do the same thing, but just much faster. So that's it. That's in the tutorial, really. You don't need to do anything. You don't need to rewrite your code. You just use the plugins, and it's great. Okay, yeah, that's not quite why we're here today. This tutorial is kind of coming at this from a different angle. But we have this thing that we talk about, we were talking about kind of GPU and Python and Rapids and things around accelerated computing swim lanes, right? So this is kind of the different layers of our stack that you can come in and work at. The very top of this stack is this zero code change. Come and load the plugin, come and load the extension. If you use polars, just turn on the polars engine. Richie's here this week giving a talk about the GPU supporting polars. There's loads of stuff where you don't need to do anything. You can just turn on the plugin and get some acceleration. And this is great because you can try this out. You can explore, you can experiment. You don't have to rewrite these existing large code bases. But we're kind of adding this acceleration in a way that is trying to be all things to all people. We've kind of written this in a way where it will try and do the best thing that it can for in that situation. If it can't run on the GPU for whatever reason, if it's something that's unsupported or something that is, some error is happening, it will fall back to the CPU. So the code will still run, you'll still get to the end, you still get the same answer, but there's a small overhead of that. And these are a great entry point to these libraries. But then as you kind of experiment and you start getting value from GPUs, you can start digging deeper down the stack of oh no, I actually want to write some code for the GPU. I know what I'm doing is like a GPU specific thing, I can get some benefits. I don't want to use this top layer of code, I want to kind of go down to the next one. I want to invoke these libraries directly. I kind of have enough understanding so I can prod and poke at the kind of the PyTorch level, TensorFlow level, XGBoost level. Or maybe you want to go deeper than that into kind of the underlying libraries that support all of these things on the Python side. And that's kind of the sweet spot for this tutorial. We're going to start at that level of what is CUDA, what is kind of parallel programming, how do I write code for the GPU, but we're starting at the Python layer and going upwards. So we're not going to be talking about any C++, we're not going to be talking about any of that kind of stuff. We're going to be starting from Python. But if you do want to keep tuning, you can go the other way as well. You can keep going down, you can move down into C++, you can use kind of the high level libraries for the acceleration, or you can go all the way down to the lower level end of things. And this is up to you, this is up to your use cases, wherever you want to be. But we tend to show that you can come in at the top, try stuff out, give it a go, use your existing code, but also you can kind of come in and tinker and tailor and do whatever you like that's most useful for you. So we're going to start in this middle layer. And my hope for this tutorial is I'm going to talk to you about kind of specific CUDA things, concepts around GPUs and programming and stuff. And you'll go away thinking, oh, I'm really glad that I learned all of that. I understand all of these things. I never really want to think about that again. I want to use the high level libraries. But I know when this is applicable. I know when this is useful. And I know that I do have the tools up my sleeve to go and dig deeper if I need to. But you shouldn't need to in many, many situations. So I've given this tutorial a few times. This kind of started when I first joined NVIDIA. I joined NVIDIA in 2019. I was an active Python developer. I work a lot on a project called Dask and a few other Python libraries. And I came into NVIDIA to work on those things because Dask is a distributed computing library, and we wanted some implementation for multi-GPU workloads, and Dask was a good fit for that. Right? So I came into NVIDIA kind of knowing about a bunch of stuff, but not knowing about GPU programming. And so I put together this tutorial as kind of a means to learn myself. I quite like to learn by teaching other people. It makes me go and dig deeper than I maybe would in order to put some material together. So I'm going to start at the beginning of this material with like the basic questions I had when I joined, when I knew nothing about GPU programming, trying to answer some fundamental questions. And then we'll kind of work out from there and talk about problems that are useful and interesting. So just so I can get a bit of a temperature for the room, can you put your hand up if you have done any kind of programming in Python that uses GPUs? I'm talking about higher level, PyTorch, TensorFlow, kind of upper level stuff. Okay, so some people. What about if we move a bit further down? Has anybody done any of the kind of lower level that involves Python GPU stuff? Okay, and then moving a little bit further down, has anybody done any like C++, CUDA, compiling code? Okay, a few folks, but I think you're like the right audience for this material. We're going to start in like this Python lab and just talk about some real fundamentals of like what is a GPU, what is the CPU, what is the CUDA programming model, how do we manage memory, all of that kind of stuff. And we'll dig through some Python libraries that you kind of understand all of that. And then we'll move up to some higher level libraries as we get through the later sessions. Don't scan that QR code, that slide was replaced by the first slide, which is this one. So I just want to check, put your hand up if you are here and you've logged in and you've got like a session running. Okay, some people, put your hand up if you're not at that point yet where you don't have anything set up. Okay, I'll give you a minute longer to kind of follow through this. You need to go and register for an account on learn.nvidia.com and then put in the code at the bottom to sign up. Is anybody having trouble with doing this or any problems? Okay, if you keep your hands up, hopefully some of my colleagues will be able to come around and give you a hand getting set up with that. Okay, while some folks are kind of finishing getting set up and everything, I'm going to kind of move on to the material and start talking through some of the intro sections of this, because it doesn't actually require you to run this material that you do. So if you do have any trouble, if you're still getting set up and you have any trouble, put your hand up, keep your hand up, somebody will come around and help you out. I'm just going to open this up. I'm going to try and make it big. Do you know if you're able to access Google Code? We do have a version of this on CuDF as well. If you have something like a firewall or some filtering blocking out, NVIDIA.com is not a huge amount we can do. You might have to buddy up with someone else and share it. Okay. If you have more trouble, put your hands up. I'm going to get started kind of talking through this material. That slide is basically the same intro slide. Right, just a couple of fundamentals here. We're running things through Jupyter. Hopefully you've come across Jupyter Notebooks at some point before. When you log into the instance, you'll see there's this folder called this GPU Python tutorial folder. If you click down into there, there's a whole load of notebooks. We're just going to run through these notebooks sequentially, opening them up one at a time. I'm going to kind of try and be careful to stop my kernel in between each one because I don't want to accidentally use a bunch of GPU memory anyway. So if you see me kind of clicking that, I'll kind of talk you through that as we go. But I'm going to try and make this as big as possible. Is this big enough for everyone? Is everybody happy? You can kind of see what we've got on the screen, seeing lots and lots. Okay, so let's dive in and first just talk about like what is the fundamental difference between a CPU and a GPU in terms of actually writing code and doing programming. Right, so the CPU is this part of your computer that you don't think a huge amount about. It's how the computer works, right? I write some code, it runs through that code sequentially. I've got a MacBook in front of me here. It's got however many CPU cores that it has, and I have an operating system on here which helps me run processes. It runs through my code. I write my Python code. I start the Python interpreter. That will then step through the code and kind of execute on the CPU, step by step, instruction by instruction. And your computer generally has like a few cores for handling this kind of thing, and various caches to help manage your memory as you're moving it around. The GPU, on the other hand, is this kind of box on the right-hand side here, with all the like small cores. The GPU is like a very different device in that it's common to think of it as like a single thing that you're getting to do a single task, but you're doing that task in parallel many, many times. Okay, so the GPU has got lots and lots of cores in it. You have all these different threads, but they're kind of all working together. They're all working to solve the same kind of problem, but with a very slight difference to kind of how each one's running. And my favorite way of kind of showing this is using this video. You'll find this on the NVIDIA YouTube channel. The Mythbusters guys did this great kind of demonstration of the difference between the CPU and the GPU. I don't know if I can play the sound very easily to the room, so I'll kind of talk over it. But they built these two robots to demonstrate. One is a CPU and one is a GPU. So this is the CPU robot. This is a paintball gun on an arm, and they're getting it to draw a picture. They've got a load of paintballs in there. It is doing one thing at a time, drawing a picture. It's just executing one instruction over and over. Then they built another very similar robot for the GPU, right? Functionally, it's doing the same thing. It's a paintball gun for drawing a picture. The difference here is it's a bit more structured in how it's put together, and it's parallel. Right? They've got all these different barrels with all these different paintballs in, and they've got this big air canister, and they've got one button to go. And the difference is they've kind of configured this machine in a way where each of these barrels is doing pretty much the same thing. They're all offset from each other. There's a slight difference. And the way they've set the initial conditions, they've loaded this with paintballs of different colors. And then they're going to run this parallel execution, right? And based on the initial conditions and the slight differences in all of the cores, the barrels in this, they're going to paint the movies. And watch that again in slow motion. This is how a GPU attacks at that problem, right? You kind of set it up, you have this parallel compute, and then you hit go, and it kind of just goes through everything in one big step. And you kind of chain those together to get these kind of big parallel execution things. So that's great. GPUs are useful parallel processors. You buy a computer, you buy a laptop, you use a server that has a GPU in it. The next question that follows all of this is like, that's great. I know how to run my Python code, right? I can write a script. I can do Python space my script. I hit enter and it runs. Like I understand conceptually it's a file that lives on my hard drive. When I run Python, it gets loaded into memory, it will do stuff. Like what is the equivalent for using a GPU? Like how do I actually talk to the thing? How do I touch the device? And I come from like a web and DevOps kind of background in the past, and one of the models mental models that I found really helped me was thinking about, well, if I'm writing code on my laptop and I want to run that code on a server somewhere, I need to move my code from here to there. I need to move my data from here to there. I need to somehow invoke the code on that machine. I need to talk to this thing. And we have all these protocols that exist, right? I can SSH into a server. I can VNC into a desktop somewhere. I can interact with this kind of remote thing. I can use FTP or SFTP or something to copy my files. I can write my code. I can use Git, right? I can push up to a repository and pull down on the server. Right? There's a route for me to get code from my laptop to the server, and there's a route for me to tell the server to run the code. And the concept for a GPU is very similar, right? You have this device inside your machine. It's connected via a PCI connection, and we need some way to move our codes to the device. We need some way to move our data to the device, and we need some way to say, go, do the thing. And that's CUDA. Right? Now, CUDA is like many things. It's it can be a bit of an overloaded term. I think a lot of people, when you talk about CUDA, are thinking like, oh yeah, the C++ kind of language stuff for writing parallel code. And it's like, well, actually, there's all this other stuff that comes to managing the device, talking to the device, moving data to it, moving data back from it. And when we're kind of talking about CUDA in the context of Python in this setting, those are the main things we're thinking about here. Is actually like, how do I write my code? How do I move it there? How do I get my data there? How do I tell the thing to go? How do I call my function? So through all of this, we're not going to worry about the C++ side of CUDA. We're just going to be talking about CUDA, Python, and the interface into a GPU from that level. And we're going to start in these low-level notebooks. So we're really going to kind of explore GPU programming, but in a Python way. So I'm going to move on to the next notebook. Can I just see like a show of hands? Everybody kind of happy, pace-wise, following along? Any immediate questions about anything that I've said?
What's the event code again?
I think you must have said
Yeah. Okay, that's a good question. Okay, where are people in terms of setup? Who has Jupyter open? Yeah. Okay. About half the room. Who is still kind of? There's like 3 steps, I guess. There's like log in, there's click start and wait for a machine, and then there's get Jupyter. Who's in there? I haven't logged in yet. I'm still logging in.
Could you put the?
Yeah, let's go back to that page. Katrina also has handouts with the same information on. Let's go back to here. Okay. Who's at there? I'm logged in and I've signed up and I've registered and I click start in the course and I'm waiting for a machine or waiting for some resource. Good, okay. That means the like pre-warning is kind of working. It will be with you. It can take a little while if you don't get one immediately. It can take a few minutes to pop up. Okay. And there's a bunch of hands for I'm in Jupyter and I'm able to run. Okay, I'm going to keep going then. But shall I forget too far out? You know, if there's a huge disparity between where you are and where I'm at, put your hand up, shout, and then we'll kind of get you up to this point. This notebook is also kind of a lot of talking, so we'll work through that and talk through that and kind of run some little bits of code. But this is kind of the first step of the code, which is, this is where I get excited. These are the bits that I find fun. Now, what I want to do in this notebook is I want to write some code in Python and run that code on the GPU, right? Very simple proposition. This is kind of the first thing I wanted to do as like a brand new individual employee. It's just like, how do I make the code do the thing? Like, I don't need to know anything kind of deeper or more complex here. So let's talk about some CUDA kind of primitive concepts that we need to make that happen. The first thing we need to do is we need to write something called a CUDA kernel. Now this isn't Linux kernel, this isn't like operating system kernel type stuff. This is kind of a bit of terminology in the CUDA world that is kind of how you hear CUDA developers talking about things. I wrote a kernel for this, or I have a kernel that does that, and a kernel that does that. So let's demystify a bit about what that means. A kernel is basically a function. Right? It's a function that we want to call on our GPU. But because of the way the GPU works, because the programming paradigm is slightly different, there's a couple of caveats that make kernel is like a subset of a function. Right? It's not just a normal function, there's a few things we have to bear in mind. And one of those things is our function can't return anything because we need to know very specifically about what is going into our kernel and what is coming out of our kernel. And if we're going to run this, you know, our device is basically going to take this function and it's going to run it over and over and over. It's going to have all these cores that are all just going to call this function at the same time. And if it's then trying to wrangle all of these return values, not fully understanding what's in all these return values, maybe being able to return something, you know, not other things, like we need to take a bit of control about inputs and outputs here, and we can't just use basic argument in, return value out. So first kind of thing about a kernel is that it can't return. What we need to do instead is we need to modify some memory. So when we call the function, we generally give it a pointer to a chunk of memory that is the input, and a pointer to a chunk of memory that is the output. And our kernel, our function, just needs to modify memory. It needs to prod these bits of memory, because these are kind of known quantities. These are things that we understand and can control, and we can handle it in a parallel space. The other thing we have to do is specify, there's a few words here, right? We need to specify kind of our grid, right? And our grid is like the number of times we want to call the function, basically. And we specify that in 2 terms. We have threads and blocks. And the reason that we do this is because, you know, the GPU is a parallel processor. It can do things in parallel, but it is a finite level of parallelism. Right? It only has X number of cores, and we can only call so many things at once. And say I have an array with 100 million things in, and I want to do an operation on each one. The GPU can't do 100 million things concurrently. It can do thousands of things concurrently. And so we're going to need to like batch through our array of data. And so our grid is kind of the overall shape of the computation. How many times do I want this to be called? And we're going to break that up into blocks of n threads. We need to decide how big our batches are and how many batches we need, basically. So there's some diagrams you can go and find on the CUDA like developer docs that kind of try and help you conceptualize the fact that you have to think about the shape and size of your computation, and then the device has however many cores it has, and there needs to be some mapping. You need to be able to chunk up your computation and run through those on the GPU, kind of as a whole unit of execution. So we'll talk a bunch in this tutorial about threads and blocks and how big our grid is and calculating how many batches we're going to need of however many threads as we go through. This is like, at least for me, this was the bit when my brain started melting when I was learning all of this stuff. And so if you feel the same way, that's fine. As we move up to higher level libraries, you will be able to get all of this again. I want to reassure you that you don't need to think about this stuff for too long, but it's interesting to think about this kind of fundamental level. Now, when we run our code, we need to, one of the first things we need to do is decide how big those batches will be. How big should those windows on our device be? And we're going to be using a few different libraries as we go through this, but one of the libraries is a library called Numba. Numba has a great CUDA section, and if you go to the Numba documentation, there's a section that just says you should use a round multiple of 128, of 32 threads in your batches, because that kind of fits inside kind of the hardware. And 128 threads is a good starting point. It's a good rule of thumb for how many threads I should put into each batch. And there are some benefits of having threads kind of batched together, because there's some shared memory they can access. Threads can communicate with each other. If you imagine you're batching through, it can help to know oh, well, these threads are executing at the same time and they want to do some communication. We're not going to stress too much about that in this tutorial. That's kind of out of bounds for what I want to talk about today. So we're just going to go with a nice rule of thumb of we're going to put 128 threads in each block. It's a nice round number. It fits on the device in kind of a regular way. And we're going to do a few things playing around with this number. But when you actually come to write this code for yourself, you might want to tune things, you might want to tweak things, you might want to go and learn about shared memory and how to do all sorts of stuff there. But we're just going to say, okay, 128 threads in a block. That means we can kind of work out all sorts of stuff later. How many computations do I want to do? I have an array with 1 million things in. I want to do 1 million computations. How many blocks of 128 am I going to need? Right, so we've kind of got these numbers to help guide us through setting up some of this execution. Now let's start with some Python that is just Python, and we'll slowly smush it in the direction of being CUDA code that can run on the GPU. And we'll kind of go through that process of seeing what it's like to transform these things. Now, one thing that I found useful conceptually is list comprehensions in Python. But I don't know if you know what a list comprehension in Python is. Okay. List comprehensions are quite a nice first mental step into GPU programming, because it's like a line of code that does a bunch of stuff in parallel. Right? It's just a for loop. You just have a list of stuff. But you think of it as it's a parallel operation. I have some kind of iterable thing, and I'm going to do the same thing to it over and over and over, and I'm going to get some result back in a list. This is kind of what we want to do on the GPU, and this is a pretty normal Python thing to do. So let's start there. I'm going to take a boring beginning point. I'm going to take the range of 10. I'm going to write a little function. This is going to eventually become our kernel. I'm going to write this function. I'm going to call it foo, and it's going to take in a number, and it's going to return that number. It's not going to do anything more exciting than that at this point. But then I'm going to write this list comprehension. I'm just going to do foo of I for I in data. I'm going to write this kind of parallel expression where I'm just going to iterate over my array, and I'm going to do something to it. I'm not going to do anything interesting, but I'm going to do something to it. Now, our first challenge here is we've already broken the rule of a kernel because we've returned something. We can't return anything from our function. So we need to think about, well, how do I get values back out of my function? So what we're going to do instead is we're going to start with our data input. And we're also going to define this output array. This is like a chunk of memory that I'm going to define somewhere. And my function is going to put stuff in it so that I'm not returning directly. And so I just modify my function slightly. Instead of returning, I'm just going to do output.append and going to stuff a value onto the end of this array. And I'm going to do exactly the same list comprehension, and we can have a look at output. So if I run this first one, we just get the numbers 0 through 9, because that's all we're kind of doing. This second one should give us exactly the same 0 through 9. But we've taken one step in the direction of writing a kernel. Right, not returning, that's great. There's another caveat which I haven't mentioned, which is that we can't have some magical unknown length array. We need like an actual concrete block of memory to put stuff into. So this is where we need to start thinking about how many times am I running my function? I need my input data to be that size, and I need my output data to be that size, and let's think about some actual blocks of memory in that sense. So to make this a little bit easier, I'm going to import NumPy, and I'm going to start off, instead of having a range of 10, I'm going to make a NumPy array with 10 in it. It's not any different, it's just this is now a NumPy array. And I'm also going to make an array of zeros that's the same shape and size as our input array. So I've got my input of 10 things, I've got this empty output of 10 things, and then I'm going to modify my function so that I'm going to update a bit of this output memory as I'm executing. And I need to decide which bit of output memory do I modify. I'm going to call this function over and over and over. We don't want them changing the same thing, they're going to stomp all over each other. We need them to modify a unique thing each time it's invoked. And so, I mean, for this very basic example, we're just going to use this. We know we have these numbers 0 through 9 as our input, so I'm just going to update memory locations 0 through 9 in this array on each time round this function call. But that's it, we're here, right? This really, really exciting piece of code here is a CUDA kernel. It doesn't return, it modifies memory, it behaves as we would expect for doing parallel code. This is like very, like, you know, my first Python function CUDA kernel. Now that I've written this, if I run this normally, it's still going to happen on the CPU, right? This is just Python, it's going to do the thing. So the next step is, how do I actually make this happen on the GPU? I need to invoke CUDA now. I need to talk to CUDA, through CUDA, however you want to describe it, to make the GPU do this for me instead. So for this, we're going to use Numba. Numba is this really great library that lets you do just-in-time compilation of Python code. It's very popular on the CPU side as well as the GPU side. It lets you write up functions and you can decorate them with this like just-in-time compiler. And Numba, when you execute it, will compile down that code and run it, you know, very fast as kind of native machine code on the CPU. Or if you're using the CUDA backend, it will compile it down into code that will run on the GPU. And this is kind of the first step of thinking, okay, we're leaving Python kind of normal how things get executed, and we're now going through this step of, I'm going to take my code, I'm going to compile it into some other representation of that, and I'm going to run it in some other way. So we'll do from Numba import CUDA, and we'll set things up exactly the same. Right? My data input array is this NumPy array, and my output array is this empty NumPy array. And now I've got my kernel here. It's gotten a little bit bigger. The first thing we've got is this CUDA.jit decorator. This is how we're saying, I want you to compile this function down to GPU code at the time that you run it. So when we execute this code. And this is kind of what differentiates it from a normal function. Now, the other thing we've been doing is we've been relying, in this example, on kind of the global namespace here, the global state. We've got this data and output variables hanging out at the top level of the notebook, and we're just prodding those directly in our kernel and in our execution. But those bits of memory are on the CPU, and we're going to run some code on the GPU. We need to like connect the dots here a little bit. And the way that we'll do that is we'll pass in those two arrays as arguments to our kernel. We're not going to pass in individual values and then use a list function. We're just going to say, I have a kernel, it takes these two arrays and it parallel processes on them. But that leaves us with, well, how do I, every time my kernel is executed, how do I decide, like, who am I? Am I kernel execution number 1? Am I kernel execution number 1000? Like, I need to know which bit of memory to read and which bit of memory to update, because every invocation of the kernel has to be unique so that they don't tread on each other's toes. And so we have this helpful function in Numba CUDA called CUDA.grid, and you're basically saying, in the grid, in our big shape of computation, who am I? What is my index within the grid? And we're specifying as an argument here that we're talking in one-dimensional terms, and we'll come on to like dimensionality in this later. There was talk about making this like an optional argument. It just defaults to 1, makes it a little easier to explain. I apologize, there's a magic number in there. But just know at this point, if you call CUDA.grid 1, it tells you where you are. If you're going to call this function 1,000 times, it tells each function, you're this one, you're this one, you're this one. You get your index of where you are within that grid. And then the last thing we need to do is actually call our function. Now, calling a function with this Numba API is very similar to calling a normal Python function, but we need to do a little bit of setup because we need to tell it how many times we want to run this function. before we had this list comprehension that had the for I in whatever kind of syntax. But this time, because we're running it through CUDA, we want to say, no, I want to run this 10 times. I know how many times I want to run it, because that's the length of my array. I want to run it 10 times. And so we're kind of first configuring our kernel. Right? We have this foo kernel defined, and we use this square bracket notation in Python to say, I want to run this many times, and we specify this with two numbers. So we say how many threads there should be in each block, and how many blocks we want. So I want one block of 10 threads. Right? This is a teeny problem. This isn't a good GPU problem. This is a teeny problem. We're just going to say, I want to do this 10 times. 128 is our magic number, and we don't need that many at all. So we're just going to have 10 threads in one block. That's how many times you want to call the function. And you could have assigned this if you really wanted to. You could have like foo configured equals that, and that becomes like our function that we can just call like any old function. But we're kind of using some Python stuff to configure this. And then you just call round brackets like you normally would, pass it in the arguments, and it runs. So load up our data, input and output. We define our kernel. Each kernel works out who it is, and then modifies that bit of memory in the output array. And then we configure and execute our kernel here. And if I run this, I get loads of warnings from Numba saying, this problem is tiny, you probably shouldn't do this way. That's fine, thanks Numba, it's a tutorial. But we get this output array. Right? That was it, we did it. We did Python on the GPU. Like, that's kind of the first step in being able to run this kind of thing. And this for me as like a new NVIDIA employee was like a really exciting moment. It was like, oh wow, I actually wrote some code that I can conceptually understand. I didn't have to go and learn C++, and then I've now executed that code on a GPU, and it's done it in parallel. And there's like all sorts of different places already that I can imagine using this. And there's a bunch of explanation that I've already talked through here. Feel free to read through that. But let's scale this up a little bit now. We talked through some basic concepts of how we run these things, but it gave us these warnings that said, your problem is too small. That's fine, that's useful. Let's do something that's not too small. So let's start with a big array, and we're going to put 30 million random numbers in a big array, and we're going to do an operation on that. So first off, let's just use NumPy again, define some big array, and I'm going to define an output array as well here. There's the same shape. And what I'm going to do is I'm going to write a list comprehension again. Let's go back to Python. Think about how nice and fast Python is with for loops. And we're going to do a very basic operation where we're going to go through every single element of the array, and we're going to double each number. And this is kind of a simple operation. But in Python, we would write this as, we're going to take a number in, we're going to put the value into our output array, and we're going to double that input array. And then we write our list comprehension that just loops over the NumPy array, doubles each item, puts it into the output array. And if I time this, last time I ran this on whatever machine I wrote this notebook on, it took about 10 seconds. I don't know how fast the CPU is on whatever VM we've got here. 8 seconds, okay, fair enough. I've gone through this 30 million long array, I've doubled each number, and it took 8 seconds to do that in pure Python. Now, I can do exactly the same thing with a bit of CUDA code. So let's rewrite that same thing. Let's take our output array. This is just a big empty array again. And now we're going to do a little bit of our maths to work out the shape of our grid. Let's define, we're using 128 threads per block, the number of batches we want to go through, or computation. Is that useful number that the documentation told us about? So let's start with that. And then I need to go, okay, I've got 30 million things in my array. I'm going to do batches of 128. How many batches do I need to process every number in my 30 million array? So I've just got a little bit of maths here to just say, work out how many blocks I need. So I've got number of threads per block, number of blocks for the computation. And I'm going to define this CUDA kernel here, where we take our input array, we take our output array. The kernel asks, who am I within the context of the grid? Which index am I? Which memory location do I operate on? It gets its index, and then it just plucks a number out of the input array, multiplies it by 2, puts it into the output array. We can then call this using the numbers we worked out before. How many blocks, how many threads, what are my arrays? And we run this, and instead of it taking 8 seconds, it takes 174 milliseconds. The GPU is parallelizing this execution, and it's chunking all the way through this. Now, Who here, if you were solving this, would have done it in the very first Python way? Can anybody think, forget all the GPU stuff, can you think of a different way of doing that same computation, doubling all the items in that array?
NumPy.
NumPy, exactly. So let's have a look at what that would look like in NumPy. It's very nice Python code in NumPy, right? I can just do my array times 2, and I can see how fast that goes. And that goes 30 milliseconds, right? NumPy is way faster, again, than what we just did on the GPU. Let's unpack a little bit about that. The first thing I want to say is, I know we went from like a small toy problem to a big problem, but in GPU terms, this still isn't a big problem. Right? Actually calculating all of those numbers is not a large thing to give a GPU to do. We're going to be working with way more data than 30 million items in an array. Because there's a bunch of overhead, right? To use the GPU, it's this device on the other end of this connection, you have to move data to it, you have to execute code on it, you have to move data back. There's like some overhead, and so you need that computation to be big enough that the overhead becomes negligible. And still, in this example, the overhead was substantial enough that we're not beating out NumPy. So let's talk a bit about some of that overhead and what that looks like. Now, one thing that you may have noticed as we've been going through is we've been working with NumPy arrays this whole time. Right? We've been keeping these arrays, calling CUDA kernels on them, modifying those arrays. But NumPy arrays live on the CPU, right? They live in your main memory. They're not anything to do with the GPU, it's just NumPy. So how does that work? What's happened here? Numba does helpful things for you. And so when you call a CUDA kernel and you give it a NumPy array, it looks at that NumPy array and goes, that's not on the GPU, I'm going to copy it into GPU memory. It then executes the CUDA kernel, and then it goes, I'm going to give that back again now. Right? So your array is going to kind of round trip through the GPU as well. But we can very explicitly tell Numba to do this for us. We can just say, no, I've got this NumPy array, I know it's in CPU memory, can you put it on the GPU for me right now? So you can do this CUDA.toDevice and pass it some piece of memory. It knows what the NumPy array is, so it copies it down to a Numba CUDA array thing. And we're going to do that for our output array as well. So we're very explicitly moving our memory intentionally now. We're not going to let Numba do automatic memory management. We're going to do it ourselves. And now if I have a look at this GPU random array thing, it doesn't show us our NumPy array, it's just a pointer. It's like, this is a pointer to a thing that's on the GPU. But that's great, we've got stuff in GPU memory. And now I can run my CUDA kernel again. Let's run it a bunch of times to see how fast that goes. And our doubling CUDA kernel has now gone down to, well, 38 microseconds. So we went from 8 seconds in Python to 100 or so milliseconds in like non-memory managed GPU. We went down to like tens of milliseconds in NumPy, and then we've gone down to microseconds with GPU code without doing this memory management. So hopefully you can see, this again is like a small example, but if we scale this up, the GPU is giving us like thousands of times acceleration on performing this calculation. So we need to feed it with loads of data to kind of make that computation time outweigh the bit of overhead that we have to do to move the memory around. Oh, the last thing we need to do is ask for the memory back, because we haven't got that back. But you can just say copy to host on a device array, and you get a NumPy array back out again. Now, the place where this becomes useful is you're often not writing a CUDA kernel, you're writing like a series of CUDA kernels. You've got some algorithm, some kind of thing that you're trying to implement, some workflow, and you're going to write different kernels that do different things, and you're going to chain them together just like you would with any other function call. And so when we write this, if we do it the naive way and let Numba manage our memory for us, it will copy memory every time we run a kernel, right? And so if I had a foo function, it would, and I just, don't need to do that. If I had a foo function and I just execute it, Numba will copy the memory to the device, do the execution, copy the memory back. They've got a bar function, so it'll copy it back to the device, do the function, move it back. I've got another function, so and memory's just like flying around all over the place, it's very wasteful. So we want to do this intentional memory management. We want to say, let's put some memory on the GPU, I'm going to call a load of kernels against it until it's in the state that I want it to be, I've got my output, and then I'm going to bring it back to the CPU. Trying to reduce that amount of time of data flying up and down the PCI bus it's easy to lose time. So that's kind of like an overview of of the Numba stuff. Next thing we have, the next notebook we have here is an exercise for you all to do, to go in and write your own kernels and kind of walk through this yourselves. So what we're going to do in this notebook is we're going to solve the FizzBuzz challenge, right? This is kind of a standard computer science problem where you are trying to take a bunch of numbers, and if that number is divisible by 3, it's fizz. If it's divisible by 5, it's buzz, and if it's divisible by 15, it's FizzBuzz. And we kind of want to go through all the numbers and just say, are you fizz, are you buzz, are you FizzBuzz, and then get some output at the end that tells us that. So there's an exercise here. I'm going to give you maybe 10 minutes. It's just coming up to 10 to 10 at the moment. So if we go up until 10 o'clock for you all to work through this exercise, myself and others can kind of float around the room. If you've got questions, put your hand up. And then at 10 o'clock, I'll kind of go through the solution to this, and we can talk about how we would implement that. Go back to the top. We're going to make our input array, right? This data array with our 50 million things in. And we're going to create our output array, this big array of zeros. And then we're going to calculate how many threads, how many blocks do we need to work through this? What's the size of our grid? So we'll use our kind of hard-coded 128 threads number, and then we'll calculate the number of blocks that we need to execute through this. We can just use the shape of the array and divide it and round it up so that we've got the right number of blocks. Now, one thing you might find, if you try to use strings in this function, you can't put strings into this kind of array, just the way that these kind of arrays work. String support is something that GPUs have traditionally not had, but there is a whole bunch of ways of doing strings, but in Numba, in this kind of array, we can't use strings. So instead, we're going to use some numerical values to represent FizzBuzz and FizzBuzz. So we just go through, we work out who am I, which invocation of the kernel am I, what's my input number, and then am I fizz, am I buzz, am I FizzBuzz. We'll put those kind of markers into the output array. So if I run these couple of cells, and then we can go through and just run our kernel to calculate that. And there was an extra credit question at the end as well, to just say what is the highest, can you work out what the highest instance of fizz is in there? Because we're in a NumPy space, we can use NumPy to do this, right? Because our output is just NumPy. I partly just wanted to demonstrate here that you can mix all of these things together, right? If there's a calculation that makes sense to parallelize, we can do on a GPU, that's great. But if there's something sequential, if there's something where we need to compare all the values, maybe we want to just keep it on the CPU. Maybe we want to do something where we use NumPy for that. Great, okay. That's the end of the second chapter, intro to Numba stuff. Now, we've got about 20 minutes left until the other sessions go for coffee break. So I'm going to get into the next section. We might not get all the way through it. We can come back to that when we come back from break. But we're going to carry on talking about Numba, but we're going to kind of think about a more useful use case for this library. Instead of just playing around with arrays of numbers in NumPy, let's actually play around with some arrays of numbers that mean things. And kind of a great way to experiment with GPU programming is kind of image-based calculations, right? GPUs were there, originally invented for graphics type stuff, and they're great at doing parallel processing. They can work over grids of numbers, and an image is just a grid of numbers, right? And so we can do all sorts of image manipulation stuff with these libraries, and let's kind of write some of this stuff from very low level. So one of the first things I'm going to do in this notebook is I'm just going to import matplotlib. We're not going to use matplotlib for anything exciting, but matplotlib has got a very nice function in there which lets you read in an image as a NumPy array. And that, given that we're starting from NumPy arrays in this tutorial, we're just going to use that function. So let's just import matplotlib. And it also can go the other way, so we can take kind of the RGB values of an image stored as a NumPy array, and we can plot that, but we can basically just render that back into an image again using matplotlib. So we're not going to do any graphing or anything, but we'll just use it for image input output because it's got a nice API. So the first thing I'm going to do is I'm going to load in an image. Right? I'm going to use the matplotlib imRead function, and I just have the Numba logo, the Numba project logo in here for something to play with. If we have a look at the type of this has been loaded as a NumPy array. If we do imshow in matplotlib, you can see we're kind of just plotting that image back out. So we've gone from a PNG into a NumPy array, and then back into whatever Jupyter's showing us, probably another PNG. Now let's do some modification to this image. Let's play around with this image, process it in some way where doing it in parallel would be beneficial. What we're going to do is we're going to do a blur on this, right? We're going to blur our image, and that's the kind of thing where we want to modify every pixel. Right? We want to go through every pixel and blur it, and so that's a great candidate for parallel processing. I'm just going to throw this image on the GPU. I'm going to write a kernel that is going to blur this image. We'll call it, and we'll get a nice blurry image. The first thing I'm going to do is I'm going to move our image down onto the device. We're going to call CUDA.toDevice. Now, when we've been calling CUDA.grid so far, we've been just giving it the magic number 1 to say we're in one-dimensional grid land. But now that we're working with an image, we might want to actually use some of the benefits of CUDA having concepts of higher dimensionality in the grid. So if I want to work with an image, it's not just a one-dimensional NumPy array. It has a shape. And we might want to think about how our calculation maps onto that shape. Right? How do we want to process it? And so when you end up writing these algorithms, it's really useful to have this mental model of what is the shape of my input data, what is the shape of my output data, and what is the shape of the computation that I need to do to get from A to B. Right? And they are not necessarily all the same thing, and we'll see a couple of examples of that as we go through. But let's first start looking at what is the shape of this image. Right? It is 116 pixels tall by 434 pixels wide, and this is by 4 deep, right? Which is the red, green, blue transparency channels of the PNG. Right? And all the values for our image are stored in this 3-dimensional array, even though it's a 2D image. The memory structure is a 3D array. And so we can define our grid as a 3-dimensional window that we're going to move over this. And you can kind of cut this up however you like. It's up to you. There are benefits and consequences to doing all sorts of different things. What I'm going to do for this is, imagine we have this 3D thing. I'm going to window over and work on little squares of the image, but I'm going to use the full depth. So each block is going to have all of the color channels in and like a little square. And you kind of think it as we're just moving this little square over the image and working on each little section piece by piece. And so I'm going to specify my number of threads that I want as a tuple here. And I'm kind of, for the last number, I'm specifying 4. I know there are 4 color channels. I want the grid to be 4 deep, and then I'm kind of moving over it in whole pieces. And then I can specify other numbers for the other 2, the shape of my window. The picture that I'm working on is wide and not that tall, so I've made the shape of this wide and not that tall. That's really arbitrary. Doesn't really matter kind of what I've done here. But the important thing is that these 3 numbers multiply together to make up the 128, right? Because this is the good rule of thumb. This is the good window size that we want. And so the GPU knows how to chunk through in batches of 128, but we're going to let it wrap up the dimensions for us. So we can start thinking about these little blocks of computation that are going to window over the image, and each one is going to operate on a single pixel. So there's a bit of nastiness there to just actually work out, if I had thread, like a little cube that I'm going to window over this thing, how many of those do I need to kind of do a convolution of my whole image, basically. And so we're just going to work that out. We work out how many threads per block and how many blocks per image do we need in order to do our full computation. And once we've got those 2 numbers, we can multiply those back out together to show, okay, the shape of our computation is 116 by 448 by 4. And we have this kind of grid of computation, and we're going to put that on top of our image, and it will overlap. You might notice here that our computation is very slightly bigger than our image. The image wasn't our nice round number, because our data never is a nice round number. And so one thing we have to bear in mind, and you might have run across this in the last notebook, is the computation will just run on whatever you tell it to be. Like you have your input data, but then you tell it how big to be, how big your computation should be. And so you can end up in a situation where the kernel goes, which thread am I? Oh, I'm thread number 116 by 448 by 4, and I'm outside of the bounds of my PNG, because the PNG is smaller than that. So what does it do in that situation? And in this case, it will carry on, right? It will just keep going within the bounds of that computation. And we'll see what that looks like in a second. And this notebook is kind of left imperfect to kind of show that to you. But let's write our kernel. This kernel here, this is our blur. And we're going to take in our image, our input array, and we have an output. This is just another empty array that we can put our blurred image into. And we're going to ask, who am I? Which thread am I within our context of our grid? But we can ask for that in 3 dimensions here. Because we've specified everything in 3 dimensions, we can say, like, who am I? What is my X, Y color channel position within the image? And I can kind of keep the concept of an image in my code, and I can write things in a way where, conceptually, my code reflects the problem. But this is where we might want to start thinking about guarding these bounds, right? Because so far, we've just been running over the edge of our bounds. And what will happen is the GPU will just go, I'm going to read a bit of memory from this address that's outside of the array. I'm going to read some memory that I probably shouldn't read. And I'm going to do something with that, and I'm going to write that to some piece of memory that I probably shouldn't write to. And Numba will tell you off if you do that too aggressively, but it does give you like a little bit of leeway. And so you can just read rubbish and write rubbish in and out of memory. There's, these are kind of, when you're working at this level of programming, aren't these memory safety things. It won't like segfault on you. It will just let you do the thing you shouldn't do. So you have to be kind of careful of that. So I've got a little bit of code here to kind of guard us going off the bounds, but you'll still see we have got a bug in here, like an out of bounds bug, that you might be able to spot in here. Now what we're going to do to calculate our blur, this is just a very simple blur. We're going to go over every pixel, and for each pixel, we're going to look at the value of all of its neighbors, and we're going to take the mean, and then we'll write that to that value in the output array. So we'll just go over every pixel, and we're kind of condensing down the surrounding pixels to blur it out. And I've tried to lay the code out here so you can almost see the shape of the little blurry window that's going over. We've got our X and Y positions, and we're just kind of offset. So we've got these 9 numbers, and we're going to divide them by 9 and assign them. And so we can write this as a CUDA kernel. Now this is one of these situations where that's not a very aggressive blur, right? Taking a pixel and calculating the average of the values around it give you like a slight blurriness, but I might want it really blurry. And so we could just call the kernel again, and call the kernel again, and call the kernel again to get like a deeper and deeper blur each time. And this is one of those cases where I don't want to be copying this picture back and forth between the CPU and the GPU every time I want to add another layer of blur. I just want to copy it down, blur it up as much as I want, and then copy it back again. And so we have a little bit of kind of Python code here, which is going to add 5 levels of blur to my image, right? I'm going to just loop over 5 times. I'm going to call my blur kernel to add a layer of blur. And so imagine I've got my input image, and I'm blurring it into my output image. And now I want to do it again. I've already got these 2 arrays in memory. So I'm just going to read the output, and I'm going to blur that back into the chunk of memory that was originally my input. And then I'll swap it around again, and I'll blur back the other way. And you're kind of just blurring values between 2 chunks of memory. I'm not making or allocating any new memory each time I add a new blur. So there's just a quick little like pointer swap here in Python, where we just switch the names of the variables, blur again. Switch the names of the variables, blur again, so that we can kind of read memory each time. And if I run through and blur it, it's nice and fast to calculate that on the image. And if I show it, we get a nice blurry image. Now you might also notice there's some kind of smushy stuff on the bottom of the image. Did anybody shout out? Did anybody spot why that's happened? Just shout out, go for it.
We're not checking at the edges.
We're not checking at the edges, right? We've got a little bit of a safety check in here to say, don't operate on pixels outside of the bounds. But then the next step, we're saying, what are my surrounding pixels? And for the pixel in the top right corner, we're reading out of the bounds of the image. And at the bottom edge, we're reading off the bottom of the image to calculate this average. And so, although we're not writing to bits of memory that we shouldn't, we're reading from bits of memory that we shouldn't. And so you get this, I need to scroll that down. We get this kind of blurriness around the edge where We're just reading random values out of RAM, nothing to do with us. They're either going to be the initial numbers that just, I don't know, what the electricity ended up as in the device when it booted, or it can be leftover memory from other kernel calls or other operations or other allocations. So we also need to think about guarding for that as well, because really there should be a nice crisp white image around the edge. We shouldn't be reading out of bounds when we're blurring along that side. So these are things to kind of take into account as you're working with these things. Now, what I'm going to say, the timing's actually gone quite well with this, because the next, I won't put the solution too fast. The next notebook is another exercise for you all, and what we're going to do is, instead of going through and blurring this image, we're going to go through and convert it to grayscale, basically. So we want to load up our image, we want to do some operation on it, and you need to think in this one about, what does my input image look like in terms of the shape of the array? What we talked about before. What does my output image look like? It's going to be the same, right, because it's an image. But what does my calculation look like? In the last one, we operated on every pixel and every channel independently, and we kind of blurred the reds, we blurred the greens, we blurred the blues, we blurred the transparency. And when you're doing a different calculation, like grayscale, you want to do that differently, right? I want to actually operate on all of the color channels at the same time, and I just want to take the average of the color channels to switch it over to grayscale. So although my input array and my output array are the same shape, my calculation in this example is a different shape to the calculation in the last one, because we want to operate on a different window, different size of stuff. So that's enough hinting on how to do it. We've got about 7 minutes until the break, so what I'm going to say is start going through this, start solving the problem. When we get to 5:30, I'll let you know, and we'll go out and have coffee, and then when we come back from the break, I'll go through the solution to this one. But we'll be around until 5:30. If you've got any more questions as you're working through this one, put your hand up. And actually, it might be worth saying, before we go, does anybody have any kind of general questions, broad questions about anything that we've talked about in the first half of this tutorial that you think might be good to talk about as a group? Yeah, go for it.
So you mentioned 128 is a good, 128 as a number of threads is a good start. So what's the progression and what's a sensible limit?
So the question, just for the recording, was we're working with this 128 threads as a good rule of thumb for how big each of our blocks should be, but like, where do we go from there? What's the next thing we want to think about? Now, different hardware has a different number of things it can do at once, and 128 is kind of the lowest common denominator in. You can grab any GPU from anywhere that's been produced in the last few years, and 128 will work. It'll work, it'll be great. There are some benefits from going to larger blocks, especially if you want to communicate between the threads within a block, if you want to use some of the shared memory or do any kind of atomic operations. And so increasing the size of the blocks can be beneficial to you in your code, but it also reduces the hardware compatibility, right? The number of GPUs that you could run that code on. Oh, you might not be able to run that on older hardware. You also might want to think about how you're constructing these computations, and how you want to shape this up. But there's all these different benefits of the shared memory, the different caches that you can use in the GPU. And so you might want to move those numbers around so that you can work on that in a different way. But it's like a very algorithm-specific thing that you're trying to think about at that point. And I said at the beginning, it's kind of out of scope for this tutorial. Partly because I don't write this kind of code day in and day out, and so I don't want to give you a terrible answer. There are people in the room who do, and probably can give you a good answer. But I encourage you to go and find them at the coffee break and ask them. There's wave if you can answer this question knowledgeably. Jacob Bradley. Yeah. So come and find these people and ask these questions at the break if you want to dig deeper. But I don't want to overwhelm. This is meant to be like a GPU Python 101. I don't want to go with too many millions of concepts that I'm going to explain badly. But if you want to know more, go and ask other folks. Go for it.
What is the relationship between Numba and CUDA?
What is the relationship between Numba and CUDA? Okay, so CUDA is an NVIDIA technology, right? It's a language, it's an API, it's a protocol. Numba is an open source Python project, right? It's come out of Anaconda, and there's a whole bunch of folks that work on it. We have people at NVIDIA that contribute to Numba. Numba's goal is to take Python code and just-in-time compile it and it can do that for a bunch of different targets, different backends. NVIDIA as an organization is kind of invested in the development of making sure that the CUDA support is really good in Numba. And so it's an open source community project, and everybody's kind of here to play and work on these things. Go for it.
So we have CPU and GPU, right? So why CPU is so weak and GPU is so powerful, and why they cannot share efficiency?
Okay. The question is why are CPUs weak and why are GPUs powerful? I mean, it's a programming paradigm, right? Like GPUs are able to do lots and lots of things at the same time because of the way that the chip is laid out, but it has limitations, it has consequences to doing that. Like you don't want a sequential algorithm that has to, each step relies on the previous step. You can't parallelize that in that way. It would be very inefficient to run that on a piece of hardware like a GPU. But there are places where CPUs excel and there are places where GPUs excel. This is why you see kind of server chips that have got both of them like fused together and kind of run code on either side with shared memory to try and reduce some of the challenges of talking between the two devices. But yeah, there's a place for each of these chips really, and like I think a lot of people in the community are used to writing CPU code, and so hopefully this is just adding a new tool to your toolbox for the times where it is valuable and useful to you.
If you go to the GitHub repository where the tutorial is, there's actually an accelerated Python user guide in there, and it actually lays out some of the pros and cons of why you want to use a CPU versus a GPU, or GPU versus a CPU. Kind of give you some hints on like which one might be the best fit for whatever algorithm you're trying to implement.
Yeah, okay, so the answer to that for the recording was if you go to the Accelerated Computing Hub, there's a great page that outlines these differences and pros and cons of when it's good to use one and not the other. Cool, yeah, next question.
How does GPU help in like I/O bound tasks like reading a file?
How does it help in I/O work?
Yeah, I/O bound tasks.
So there's different aspects of I/O operations. I mean, if you imagine I've got some data on a hard drive, and I need to read that into memory and do some calculation on it. The typical way of writing this kind of code, we've been constructing these arrays, right, from nothingness. But if it was actually an array on my hard drive, I would have to load it into the CPU, and then down onto the GPU, and then do my calculation, and then probably put the result back onto the CPU to then give some feedback, some answer somewhere. So the like very naive answer is just that like using a GPU adds a bit of a delay into loading data from disk, right? I/O can be a bit slower. And so there's all sorts of other stuff in here that you need to take into consideration. One is that we have a technology called GPU direct storage. This is a way for the GPU to talk directly to an NVMe hard drive and load data from the disk straight into the GPU memory without the CPU even being involved or whatever. So you've got these two devices that are both connected to the PCI bus, and you can move memory between them. So you get some nice you can get some great performance acceleration there by moving data in parallel to the GPU and then processing it in parallel. The other thing around I/O is lots of common I/O involves some kind of computation. Right? And one that comes up a bunch, especially if you're kind of like from the financial sector, is as much as you hate it, you might still have to use CSV for things. You get files given to you in CSV. It's a very popular format. And one of the things about CSV is there's no type information, and like columns don't have to be of a single type. So when you load a CSV into memory, you have to read the raw ASCII value from the file, put it into memory, then look at that value and say, what is this? Is it an integer? Is it a string? Is it you have to do a bit of compute to work out what type is this. And you have to do that for every single value that you load from the CSV. And we do that on the CPU. But that's a perfectly parallelizable problem, right? We only need to work on each value in the CSV independently, and we can run that on a GPU really nicely. So if you have a look at one of these libraries like cuDF, the CSV reader in cuDF is super fast compared to the CSV reader in other libraries like Pandas, because you can parallelize out this step of like I/O. So there's loads of places where you can get I/O benefits from GPUs, and other places where it adds an extra hop, and you have to kind of think about these things and work out how it fits your use case. Got a question over there?
If you could just explain the threads and blocks, it's actually, I know you've worked with it, but
Yeah, that's fine. We can go over threads and blocks again. It's one of those things I think that takes a lot of time to get used to. But when you're writing these computations, you need to decide, I have a function, my kernel, I'm going to need to call it some number of times in order to do the thing I'm going to do. So on this image, this picture that I've got, I know that I'm going to need to call it for every single pixel in my image. And we refer to that as the grid size, right? The total number of times that I want to call this function is the size of my grid. And then that doesn't necessarily map to the hardware itself. Like the GPU can do a certain number of things in parallel, but it's only got so many cores. And each device, each NVIDIA GPU that you can go and buy, slightly differs in the number of CUDA cores that it has and how it's kind of broken up in the hardware. So the way that we handle that is we take our overall grid and we break it up into batches, small batches that we know we can work through on any GPU. And so you go and get a low-end GPU and maybe you can do 10 batches at once. You're going to get a high-end GPU, maybe you can do 30 batches at once. But it doesn't matter, you've broken up your overall computation into batches, and those batches are what we call the blocks, right? So the grid is the overall computation, the blocks are the batches that we're going to work through, that the device is going to work through. And then the threads is like, the number, I like how big the block is. So the default rule of thumb in here is that our block is going to have 128 threads in it, just because that maps to the actual hardware quite well. So you take your overall image, you break it down into batches of a certain size, and those words are just the terminology that we use to represent that. Okay, I make it coffee time. Please feel free to keep plugging through that exercise. Maybe we'll have 5 more minutes when we come back as well. If you've been listening to this Q&A rather than working through the exercise, and then we'll go through the solution. So I hope this has been useful so far. Please go and enjoy coffee. If you have any more questions, come and plug any of us NVIDIA folks while we're. So we left this on the black and white, or the grayscale lab. So let's dive into the solution for this one, which is this 3.2 notebook here. One of the questions that came up in the break was talking about the input array and the output array and the grid. And so this notebook is intended to kind of stretch that concept a little bit more. So we're going to start out very much like we did with the blurring example. We're going to import matplotlib. We're going to load in this Numba logo just for something to play with. And we're going to move it down onto the GPU. Right? CUDA.toDevice, go on the GPU. And we'll create this output array on the GPU as well. The one thing that I often get asked when talking about this is efficiently assigning these arrays. And so throughout this tutorial, we make these NumPy zeros-like arrays. And that's partly in there to like trip you up a little bit because that's like not the most efficient thing you could do. Like we're allocating an array in memory on the CPU, we're filling it full of zeros, and then we're copying all of those zeros down onto the GPU, which is an inefficient thing to do. So if you've had that thought of like, why are we doing that? You don't have to do that. I wanted you to have that thought. There is another operation you can do where you just say empty like, or you can use numbers like array allocation directly. We don't need to make a NumPy array and copy it. We just say, I want a new GPU array that's empty. And that's a very fast allocation compared to copying stuff around. But this notebook is intended to make you think that, so we're going to still do some nasty zeros and things. But the next thing we're going to do is we're going to think about our grid. What shape is our grid? What do we want our blocks to look like? How are we going to operate over our image? And in this example, we want to take this mean across the red, green, and blue channels. So we don't want a 3-dimensional grid this time. We don't want to operate on every pixel in every channel and do some blur operation. We want to go through every x, y value and kind of collapse one of the dimensions almost. Right? And so we want a 2-dimensional grid. We're going to kind of window over this thing in a 2-dimensional way. So this time, instead of specifying our tuple with 3 things in, we're going to specify a tuple with 2 things in to specify our little window size. And again, we want these to multiply to 128 because that's our nice rule of thumb number. And so I've arbitrarily chosen 16 by 16 because those 2 things multiply to 128. These can be whatever you want. And at some point, as you get deeper into this, they will become useful numbers for you to tune and experiment with. But at the time being, I chose them because they are the same number and I can type them quickly. So we've got our threads per block, 16 by 16 blocks, and then we just need to work out, okay, I've got this image, it's that big, how many windows do I need to cover my whole image? So we just do a little bit of maths, and we get our threads per block and blocks per grid. Now the next thing we're going to do is define our kernel. So we've got a nice Python function here, and we're going to ask This time for our CUDA.grid2, we're in two-dimensional space, we have a two-dimensional grid. I would like my two-dimensional position within this grid. And so I'm just going to get an X and Y value out. Again, same as the last one, because we're working with round numbers and we have this nice rule of thumb number of 128, and we're rounding up, the grid is going to end up slightly bigger than the image so that it all fits inside. We don't want to calculate anything for those pixels that are out of bounds. So we've got a little bound check here to just say, if you are a thread that is out of bounds, if you've been told your position down in the right-hand corner and that's off the edge of the image, just don't do anything. Just end right with this if statement here. And what we're going to do is we're going to just calculate the average value from the red, green, and blue channels. We'll read the value from red, we'll read the value from green, we'll read the value from blue, we take the mean, and then we'll just update in the output array red, green, and blue to all be that same value. When red, green, and blue are all the same, they are a gray color. So we calculate our average in one step and then write it out in the next step. Now we don't want to take the average, we don't want the transparency to be involved in this computation because that is not the point. So we're just going to directly pass through that value, because you've got to remember we are reading an input image and writing an output image. So even though we're not operating or calculating with that value, that transparency value, we still need to copy it into the output array. So we're just going to move that across there. And if I define that and run the kernel, again, we're going to configure it with these square brackets. I have a function, this is how many times I want to call it, and these are the arguments I'm going to call it with. We run that on the GPU, and then if we plot the image, we get a gray number. So hopefully, for those of you that did the notebook, you got to the same kind of place here. Now this is kind of the end of the first half of the tutorial. So I see some hands, let's answer some questions before we move on. Go for it.
So is it possible to write NumPy functions inside the kernel? Because that blew up at me.
Okay, the question is, can you write NumPy functions inside the kernel?
We'll
We'll use
use
NumPy functions. Now, when you write these kernels and you decorate it with that CUDA.grid, Numba's going to take that Python code and it's going to lower it down through a few different representations. Numba does things like convert it to Python bytecode and then convert that to like compiler level bytecode that like a compiler like LLVM or MVCC or something can understand, and then it will compile that down to machine code, and it does that at runtime. And that means that because we're going through these different operations, some of the Python stuff you can't map directly. And so the stuff inside the function can only be a subset of the Python language. The Numba documentation is really great, talking you through what it does support, what it doesn't support, and the various folks working on that project are adding stuff all the time. I think some things can be used, like some stuff from NumPy can be used inside the kernel because it knows, like, oh, I know what that is. I know how to map that onto whatever the actual code is I need to run. But it's kind of those things are added piece by piece by piece. So it's not uncommon to run into, I wrote some, I defined a class somewhere and I tried to use that class inside my kernel and everything exploded because it has no idea what this thing is. So you're best off to try and work with like primitive types and things in Python. Cool. Any other questions before we move on from Numba onto other topics? At the back.
Along that line, can you give it a third argument? So you have input, output, and you give it other things?
Yeah, you can give, when you call a kernel, it can take any number of arguments. Maybe you might want to have like an input and output and some multiplier or some other value that you're taking into account. These are just pointers to memory that you want to reference from within the function, whether you're reading from it or writing to it. You can kind of, it's just like writing any other function. You do it how you think.
Are there any restrictions, like it has to be something that can be copied?
Okay, yeah, the question is, are there any restrictions about the type of the argument? It does have to be something that can be copied to the GPU, right? And so, like that, again, it's like a subset of things. NumPy arrays, it understands. We'll get onto like CuPy and other libraries as well, but like, you might find things like strings are not supported. You can't pass it like a list of strings, it would be sounding like that. And you get nice type errors that explode and you have to go and dig through that in the documentation. But this is kind of exactly why, like the goal of this tutorial is to start at the very top and be like, you can play with this stuff without changing your code. Now we're going to jump down to the bottom of like the Python tier and talk about some of these fundamentals and why they're kind of done that way, how the hardware works. We've talked about grids and we've talked about kernels and we've talked about all these other things. And my hope from going through this section is that that's that's not a thing that you're going to actually want to use on a day-to-day basis. There's loads of other higher level APIs that are probably more useful for you to get the thing done that you want to do. And the whole next section of the tutorial is to dig into that and kind of go more into higher level APIs. But I'm hoping this has kind of given you a bit of a different mental paradigm to think about these coding problems. And like I found learning this stuff, it was a similar feeling to when I learned NumPy. Right, going through that like mental leap of writing kind of vectorized code in NumPy and thinking about that slightly different paradigm. This is like the shift in further in that direction. I'm like, okay, I know I'm doing this operation, I'm working on an array, maybe it needs to move that. Yeah, as I'm learning these things, I'm getting a good idea of when GPUs are powerful, when they're useful. Right? They're great at these embarrassingly parallel problems. They're great when there's little interaction between each operation that you're trying to do. As you move into like shared memory and dealing with blocks and things talking to each other, like you can of course do algorithms where your threads are communicating with each other and synchronizing and doing all sorts of stuff. But this stuff excels in kind of embarrassingly parallel workloads. And so by building out some of these basic ones, I'm hoping that you'll be able to reason about problems that you see in the future. And say, okay, this thing, I could imagine how I would write this as a CUDA kernel, or this sounds like the kind of thing that NVIDIA person was talking about that I could do as a kernel in Numba. So if I use some GPU library in Python that is like one of these accelerated GPU libraries, that's probably a good fit. I can imagine how it would fit if I was going to write this from scratch. I don't really want to write this from scratch. I'm going to go and use a library that does this for me, but I know what is a good option in there. So please don't be overwhelmed or put off by digging this deep into Numba. Like you can keep going much further. There's a long chapters all the way down. Right? But from now we're going to start moving back up the stack of like where can you actually interface with stuff? Where can you poke around? Now there was a question that came up during the break, which was, I've been telling you this whole time that we've been writing code that's been running on the GPU, but like, how can you be sure that it's actually running on the GPU? Like, I'm telling you it is, and I promise you it is, but like, it just looks like code. You're just writing code, you're running code, you're getting inputs and outputs, and some things you're doing, say GPU in and CUDA and stuff. But like, how do I actually prod and poke the device and really see what's going on? Now, unfortunately, my Jupyter thing here in my container that we built for this tutorial is slightly broken, and I'm sad about that. But we have a plugin for Jupyter that shows you statistics about the GPUs in your machine. And it should be next to the little folder icon over here somewhere. There should be a little GPU icon, and I don't quite know what happened to my container, but maybe the plugin isn't installed or something. It was installed last time I tested this. But you can kind of see in this GIF that I have here, there's a couple of plugins installed. One of them is this GPU plugin, the second one down. And it lets you open these graphs here. And one of them you can see is GPU utilization over on the top right. There's GPU memory underneath that. There's PCI throughput underneath that. These are kind of statistics about the GPU that you can look at to understand. It's like opening Task Manager, or it's like calling top, or whatever it is. I want to look at my hardware and see how it's being utilized. And so this is running on a server that's got 8 GPUs in. We're doing some reasonable workload on it. And it shows you what percentage the GPUs are being utilized when I'm running my code. I can see how much memory of my GPUs are being used. And I can see my PCI throughput, right? This is how data is moving back and forth through between the CPU and the GPU. And so you can start to get ideas of where are my bottlenecks in my code. Am I running this and the utilization hits 100% and it's just fully pegged at 100%? I know this is a compute bound problem that is stressing the GPU. Maybe my memory is filling up and filling up and filling up, and then it explodes and it goes away, and I'm going out of memory on the GPU because I don't have the same kind of swap and spilling that you might have on a CPU in your operating system. To be able to see that. Or maybe your PCI throughput is like through the roof and your utilization's low, and you're like, oh, I'm just spending loads of time copying data around, and maybe something's gone wrong. So there's all these different tools that exist. This Jupyter plugin is a great one. There's also a bunch of command line tools if you use like Top or Glances or whatever. There are other things, there's like MV Top, and the Glances has got a GPU plugin. And there's these great libraries for kind of seeing and understanding the utilization. If you're on a Windows machine using WSL or something, you can see stuff in Task Manager. There's like all sorts of different options for seeing things. But you might also want to go a little bit deeper. Say you're working on a project where you have some platform or something where this isn't supported. This notebook is kind of intended to show you like how we're actually getting these numbers. These plots in the Jupyter thing, these are just like OK graphs, right? This is all just kind of PyData-y things. We're just reading some values from the GPU and then we're plotting them with OK and putting it in a little widget in Jupyter using the Jupyter plugin thing. So just to show you a little bit, if you ever feel like implementing your own kind of thing or poking at the GPU directly, we have this library called PyNVML. This comes as part of the like NVIDIA driver. There's like MVML, which is an NVIDIA markup language. You can interact with the GPU and ask it questions. And then we have a library. You need to pip install. It's called NVIDIA ML Py, is the library that gets published by the driver team. And you import it as PyNVML. Very slightly confusing because the package name is different to the import name. But you import PyNVML. And then through this Python API, you can ask the GPU questions about itself, basically. So the first thing we have to do, it's a reasonably low-level library, but you import PyNVML and you do NVML init. You just say, like, I'm here, I want to talk to the GPU. And then you could do calls like device get count. How many GPUs do I have? And so this will return and say, I have one GPU. You might say, system get driver version. Like, what is my NVIDIA driver version? Say I'm using PyTorch and it supports a certain version. Like, this is a way that you can ask it, what driver version do I have? And then we can actually, like, that's kind of system level. You're asking what the driver version is, what the CUDA version is, how many GPUs do I have? And then you can go through each GPU if you have more than one and kind of ask it various questions. So the first thing we need to do is we need to get like a handle. It's this object that represents the GPU for each GPU. So I just have a little bit of code here that just says, how many GPUs do I have? Let's get handle by index for each GPU, and I'm going to get this little list, which is my GPU. So on this tutorial machine, I should just get one GPU object. If you're on a bigger server, you'll get a list of more than one GPU object. And then we can say things like, well, get the name of the device. Which GPU do I actually have? And I'll do all these in list comprehensions to work on multi-GPU systems. But if I do this, it just says, oh, this is the NVIDIA A10G. Right? I think these tutorial instances that you're running on have probably been spun up on AWS or something, and it's just using a machine type that's got an A10G in it. But this could say T4, it can say A100, it can say H100, whatever GPU you're using. And then you can ask specific questions about, like, how much memory do you have? How much memory is being used? How much memory is free? And so asking these questions, we can see, oh, I'm using 3 gig of memory. I've got all these notebooks open, and I allocated all these arrays with my 50 million things in and whatever else, right? I've used up 3 gig of GPU memory, and I can see I've got 20 gig free, and this is probably a 24 gig card. And this is where we're getting these numbers from, that we're then putting in these graphs. If you work with systems that have monitoring, Prometheus, like monitoring systems or something, like there's all sorts of tools and exporters for taking these numbers and putting them somewhere you can see them. The other thing you could do, if you've not seen it before, is there's a command line tool called NVIDIA SMI. This tends to be the kind of hello world of, have I actually installed drivers? Do I actually have a GPU? And this gives you a bunch of information about what's going on in the GPU. So this is usually when I spin up a machine with a GPU in it, the first thing I do is open a terminal and run NVIDIA SMI, and it just prints out like, oh yeah, there's one GPU, this is your driver version, this is how much memory you've got. These are all using those same APIs to just ask information about the device that you have. Okay, that's kind of a brief aside into monitoring and understanding kind of what the GPU is doing. If you're working in a GPU environment, I really recommend that the plugin is a really great way to just see in the dashboard what's going on. Yeah, go on with the question.
How intrusive is this when you're running things?
How intrusive is it?
Yes.
Do you mean in terms of performance and things?
No, in terms of like, running something that when I track things, like it doesn't add any overhead to the current process that it's running.
No, it shouldn't. This is just small kind of. It's like opening a task manager on your computer, right? It just shows you what it's doing. Okay. Any more questions about this topic? Good. Okay. Next, let's talk a bit about interoperability. So there's a whole bunch of higher level libraries than where we've been working. We've been working with Numba so far, but if you think of Python and GPUs, you probably think of libraries like PyTorch, you think of TensorFlow, you think of CuPy, you think of all these other libraries that exist. And they each have their own community, they have their own kind of thing that they're trying to solve, and examples, and all that kind of stuff. And when you're actually trying to get something done, when you're trying to do some piece of work, you end up maybe thinking, oh, I want to use a couple of these. I want to load some data in this library. I know NumPy, I want to use CuPy to load my library, and then my data, and then I want to play with it, and then I want to move it into PyTorch as a tensor, and then I want to do some training. Well, moving around in this space is something that the Rapids folks at NVIDIA have been working really hard to try and make this as smooth as possible and try and really unite this kind of Python GPU community. And so everything we've done so far with Numba is we've had NumPy arrays on the CPU, and we've moved them to Numba device arrays on the GPU. This device array is just an array of memory on the GPU. And in the Python space, that's kind of an array with a bit of Python-y, wrapper-y stuff to just say what it is, what its memory address is, how do I talk to it, what methods does it have, how do I interact with it, all those kind of things. And that's basically all these libraries are doing, right? A PyTorch tensor and a CuPy array and a Numba array, they're all just the same memory representation on the GPU, just in slightly different clothing, and they have different implementations of methods that you can call on them. And so something that's kind of been worked on heavily over the last few years is just making sure that I want to be able to cast one to the other. I want to take an array in Numba that I've created and done something with, and I just want to turn that into a PyTorch tensor so that I can go and do the next thing. And I just want to literally cast it directly. I don't have to do any kind of magiciness. And so there's two things that exist for that. One is something we have called the CUDA array interface. This is kind of a hidden method that you implement on, like the library maintainer implements. And it kind of describes the array in a common way. It says, there's an array of data, it's this big, it lives here in memory, and then another library can come along, it can inspect that metadata, and then it can construct its own object that points at that same array, that same thing in memory. And so you can easily move around between the different libraries. There's also another format called DLPack, which you may come across if you play with any of these things, which is another like intermediate representation, but you kind of have to step from, I have an array, I'm going to make a DLPack representation of that, and then I'm going to convert that into some other array of some other library type. But the key thing here is, I don't want to copy memory, right? If I've got a 24 gig GPU in the cloud, and I've loaded 18 gig of memory into it in an array, I don't want to copy that. I don't want to make unnecessary copies as I move between libraries. I don't want to create a PyTorch tensor and allocate a whole new array and copy all my bytes across. I just want to leave that array alone on the GPU and just put it in new clothes so that I can work with some other library, some other API to get some feature that I need. So let's kind of play with that a little bit. We're going to start with CuPy, which is the library. We've not touched on CuPy yet. We're going to get more into that in a minute. But CuPy is NumPy, but re-implemented for the GPU. The API is exactly the same. There's like a couple of tiny little differences that may need to stop you from shooting yourself in the foot. You may come across them as you work with CuPy, but it follows the same API as NumPy. So if you already know NumPy, you know CuPy. We can import CuPy as CP. We can make a big array in exactly the same way that we would with NumPy. And it does all sorts of clever stuff, like it's allocated this on the GPU, it's made this, but then when I've tried to look at it in Python, it's gone, oh, I'm going to copy a little bit of this array back, just enough to construct the representation to print out on the screen. There's lots of like quality of life stuff to make it more pleasant to work with these arrays. You might remember the number array, when we printed that, it just said, this is a number array, whereas this has actually got, here's a little snippet of the values, because that's what NumPy does, so we'll behave the same way. But it does it efficiently and whatever. So we can have a look at the type. This is just a CuPy.nd array. But then I can say, well, I want to now write a number kernel. Right? We've been working with these kernels, we've been playing around. I've got this array, it's a CuPy array. Like, how do I use that in Numba? And so we can call this CUDA.toDevice, same as we were doing with the NumPy arrays, but we're going to pass it this CuPy array. A Numba will just look at that and go, oh, that's already on the GPU. I don't actually need to do anything. I'll just make a new object that's a number array. And so I print that out, and we get the same number array. So I now have two objects. I have a CuPy array, and I have a number array. They're both Python objects that I can work with. I can use their APIs. They're pointing to the same set of memory on the GPU. So I can do operations in either one, and they'll operate on that same piece of memory. I can kind of mix and match the libraries, do whatever I want to do here. And then just for fun, say, well, let's add PyTorch as well. I think PyTorch should be, no. This is why the plugin went away as well. I wanted PyTorch too. That's sad. Okay, pretend this worked. If I import PyTorch, I can do torch.asTensor. I can give it my array. I can say device equals CUDA. And PyTorch will do the same thing. We'll look at this and go, that's already a GPU array. I just need to make a new tensor object and point it at that array. And then I can print out and see that I've got this PyTorch tensor. And so I've got these 3 different Python objects with 3 different APIs with all these great features that I want to use for building whatever it is. And they're all interconnected, they're using the same memory, and I can pass between different libraries. And so this has been a huge thing for the community, I think, to make sure that it's not painful to kind of learn GPU development in Python through each of these different libraries, and you be in like a different world and a different community. Like all of this is interconnected. You can learn any one of these libraries, you can learn multiple of these libraries, you can mix and match, you can do all sorts of fun stuff with it. If you have it installed, anyway. So we should have CuPy and other things installed, so hopefully that won't happen again. But this next notebook, we're going to talk about CuPy itself. Yes, we've got a question before we go on.
So if the memory representation is shared,
yeah.
If I make changes to the torch array, would that also change the original array?
Yes, that's correct. So if you have these different objects that point at the same array, if I do an operation in torch that modifies the memory, and then I access that memory through the CuPy object, it will be the new, because we're just pointing at the same bytes in RAM, basically. So it's great if you want to, you're working in CuPy and then you're like, I really wish I had this function. Torch has got that function. It's not implemented in this library. I'm just going to import Torch, wrap it up, do the thing. Maybe I want to carry on with CuPy. Maybe I'm now in Torch. Like, whatever you want to do, you can kind of mix and match. Okay, so let's talk about CuPy. CuPy is this great project which has re-implemented the NumPy API. But they've kind of written all of these kernels for you. You don't have to worry about the implementations, you don't have to worry about grids, you don't have to worry about blocks, you don't have to, CuPy handles all of this. It makes sensible decisions on your behalf. You just use the NumPy API, and it works out how to parallelize that with the GPU using its kind of re-implementation. So the goal here is that it's not quite zero code change, as in if you want to use CuPy, you need to use CuPy. But in a lot of times you can do import CuPy as NP. Carry on, that's fine. That's totally a thing you can do. There are a couple of gotchas, but not too many. Or you can just, if you're working at a higher level, if you're working in a library that uses NumPy arrays, you should be able to just pass a CuPy array in, and it will call the same functions on it, and it will do the same things to it. And those functions should be implemented, and they should exist, and you'll just get the GPU accelerated version of the implementation. So I'm going to import NumPy and CuPy and just try and demonstrate a little bit about some of the differences here. I kind of show you some things that might be not obvious. One thing I'm going to do is I'm going to call this very long function here. One thing that CuPy does, which is really nice, is it dispatches stuff for you, and sometimes it comes back from the function call while the GPU is still busy, so that you can get on with the next piece of Python code and kind of chain stuff together, and it can do clever things. But that does mean you can cheat in benchmarks, and you can say, wow, that was incredibly fast because I called this function and it returned immediately, and I'm carrying on. So every now and again, I'm going to call this little synchronized function just so that I don't cheat in these benchmarks, basically, and I'm just going to say, wait for the GPU to be done before we move on. So let's start out. Let's create an 8 gig array on both the CPU and the GPU in NumPy and CuPy. So I'll do it first with NumPy. We're just going to do np.ones of some array, and I've just got this timer call here, which is going to allocate how much time and tell me how fast it was. So that was 237 milliseconds. And so if you think about NumPy, that's going to create a big chunk of memory on the CPU, and it's going to go through and populate all of these ones into that array, which is a parallelizable thing, right? So we can do the same on the GPU. We can do cp.ones, and it'll allocate this array on the GPU, and then we have a little kernel that's just going to batch, smush some ones into this memory, right? And all the cores in the GPU could just be ramming ones into RAM. And so it's much faster, right? We can see that this is nice and fast to just allocate memory in this way. But it was the same call, right? It's just cp.ones instead of np.ones. CuPy's doing the heavy lifting here. It's working out when to do these things. But then because of all of this, we can use the NumPy syntax that people know and love, right? If I want to multiply all of the items in my array by 5, I can just do array times equals 5, as you would do in NumPy. We don't have to think about allocating new arrays and writing a kernel and multiplying by 5 and writing whatever. We like NumPy. NumPy's got a nice API. Let's do that. I thought we merged the fix for this. Okay, the timer makes the assignment not work. We did make that fix, and I don't know why it's not here. Okay. So I can times equals 5 the CPU array, and that took 100 milliseconds to go through every element in the CPU, and times it by 5. We can do the same on the GPU, and it took a bit of time to go through and do that. And you'll notice in this example, it took a little bit longer to do that. And this is where some of this overhead starts to show through. I'm doing like a small operation. There are some small amounts of overhead. I think some of that's like CUDA setup stuff, so if I run it again, it goes much faster. Like there was a bit of warm-up time in that first call. So there's sometimes where you see these results and you think like, oh, I'm playing around with this in a notebook and this is a bit strange. But kind of as you use it more and more for like larger problems and you run the same code over and over and you call the same function over and over, kind of some of these weird warm-up things go away. But I wanted to show you this just to kind of signal and demonstrate that you may see things that are a bit odd, and this is just partly that you're working with this other device. There is some overhead with working with this device, and sometimes that shows through and outweighs the actual computation that's happening. We kind of, when we were doing the number stuff, we were seeing what those overheads were, and we could measure them, and we could poke at them. As you move up into the higher level APIs, sometimes that's abstracted away from you, and you need to run things a few times to see that benefit. Now we can do a couple of operations kind of one by one, and this is to kind of show you, like, if I times equal the CPU array by 5, and then we times equal it by itself, and then we plus equal it by itself. In our number operations, that would have done a load of like memory copying, right? Between each call, it would have copied the memory and back and forth and added all this overhead. So this cell is just kind of demonstrate that CuPy handles all this for you, right? It keeps the memory on the GPU. It doesn't suffer that same overhead. It's only when you need the results back that it actually does a copy. And you can see you get some great performance, because doing multiply operations or add operations or anything like this is very parallelizable, and the GPU can really run through it. But then also to highlight, like, the folks that work on CuPy have spent a bunch of time re-implementing like, linear algebra libraries and all these other algorithms which you would expect to exist in a NumPy-like thing. And some of these operations, you might think, that's not embarrassingly parallel. Like, is this actually going to benefit from the GPU? Because it's not like perfectly embarrassingly parallel. And this is where these people have come in and they've used these other features, these shared memory features. They've leveraged the blocks and the inter-thread communication and all these kind of things to handle the situations where they're just trying to get the best performance you possibly can out of these things. And so if I do something like calculate an SVD in both things, some things are faster, some things are slower. They're all kind of much for muchness. I don't know why that's interesting. Usually that was one of the ones where I run it and it goes a bit slower, and then I run it again and it's a bit faster. But maybe it's just the GPU. But there's all these kind of situations where it is a drop-in replacement. Sometimes things are comparable, some things are much faster, and some things you wouldn't necessarily expect to be faster are. Now the other thing that's really neat about the NumPy API is they have this concept of dispatching within NumPy. And so if you do any operation where it's like np dot some method, and I'm going to give it an array, and it's going to do the thing to the array, like NumPy has stuff built into all of these operations where if you give it a NumPy array, it goes, yeah, it's a NumPy array, I'm going to do this thing. But if you give it something that's not a NumPy array, it has a look at the thing and goes, what is this? Like, is this another NumPy-like thing? And has it got this method, and can I just call that instead? And so this is really neat where I can create a GPU array with CuPy, but then I can just use np.whatever to actually operate on that. And so this would do dispatching under the hood. I call a NumPy operation on a CuPy array, and NumPy will just go, oh, that's not a NumPy array, I'm going to call the CuPy implementation of this same function. I'm going to dispatch that off to the library where this came from. And this is the kind of situation where it's really nice, where you've built a code base that uses NumPy, and you just want to experiment with, what if I load my data with CuPy and then try poking it into my existing code that already exists? It should just pass through and kind of dispatch all the calls out in there. One of the only times that this can be challenging is it's very common in these libraries. We see this. I saw this a lot in X-ray. I don't know if anybody here uses X-ray, but when we were adding some of the CuPy support in X-ray initially, it often calls mp.asArray on the arrays that you pass it, and this is partly so that you can pass in like an integer or a float or something, and it knows like, oh, I'm going to make that an array before I do a thing to it. And this is one of the situations where CuPy will explode. If you try and do mp.asArray on a CuPy array, CuPy will raise an exception and say, you probably don't want to do that. You're copying GPU memory back to the CPU. You're converting this CuPy array to a NumPy array, and you've done it naively, and you probably didn't mean to do that, and you'll be sad if you do that. And so this is one of the situations where if you call mp.asArray on a NumPy array, it just is a no-op. If you call it on a CuPy array, it's an exception. So if you use that in your code anywhere, it will tell you, don't do that, this is going to be inefficient. It doesn't let you do the slow thing, it tells you. And so there's a very slight API difference where you have to do CP, like CuPy.get on the array to like convert it back to NumPy, and it's just so that you're very intentional about when you go back to NumPy. But it means that some libraries have to go through and think about like, oh, I need to handle this case, this use case. So worth highlighting here. The other thing about CuPy is if you have more than one GPU, you might want to be explicit about which GPU you're creating your array on, and CuPy has a way of doing this. A lot of these libraries have a kind of an intentional way of doing this. And so CuPy's method for doing that is you do CuPy.CUDA.device, and you tell it which device you want to create the array on. And then you can kind of see like, oh, this array has been allocated and it is on GPU 0. This is one of those situations where I'm on a machine that's got a few GPUs and I want to create arrays on each one, do more parallel things. But like PyTorch has the same concept, CuPy has the same concept, and has the same concept. You kind of say like which device you want it to be. So that's kind of the end of me showing you about CuPy. There's now a lab, so we're at 11:30. Let me just check where we're coming up to. So our session is going to finish at around 12:30 for lunch. Yeah, it looks like just before 12:30. So we're kind of doing well in terms of pacing. Is everybody happy with like pacing? Not too fast, not too slow. I'm seeing lots of nods. It's good. Okay, we'll go through the lab then. I'll give you 10 minutes to kind of work through. This lab is more testing your NumPy knowledge than your CuPy knowledge because it's just asking you how to do some things in CuPy, but it's the same API. So go through, have a play, see how it works. Put your hand up if you've got any questions. Me and other folks will wander around and answer. Was that a question about, like a general question? Yeah, go for it.
Where do you determine like how many number of GPUs to deploy?
Where do you determine that?
Or where do you like specify that?
I mean, it's up to, the question was where do you specify how many GPUs to deploy? I mean, like if you buy a laptop with a GPU in it, you have a laptop with a GPU in it, right? If you buy a desktop with 2 GPUs in it, you have 2 GPUs in it. It's like a hardware configuration thing. If you're using AWS and you want to spin up a server, like it's in the instance, like they've got all different size instances. Some of them come with 1 GPU, some of them come with 2, 4, 8. Like it depends which VM you choose on which cloud. For this tutorial, like this is just whatever the NVIDIA training thing is. It's chosen one for us that has 1 APU. But as you deploy code, as you run code, it's up to you to decide what, whether you're buying hardware, whether you're using cloud hardware or whatever. You make those choices at that point. Cool. Okay. Well, go through the lab. I'll wander around. Shout if you have any questions. Yeah. Okay. So when you start these sessions in the NVIDIA DLI thing, I think they time out after 3 hours. So I set mine up before you all arrived, so I probably have it timed out now. Let's just let that wake up and then we can. Yeah, I like the solution. Let's just. Okay, while that's coming up, I'm going to go off road a little bit and just. The next library we're going to talk about after CuPy, we're going to do the solution when this wakes up again. But the next thing we're going to talk about is cuDF. So we talked about pandas earlier, and like right in the beginning of this, we talked about the plugin for pandas that make pandas go fast. I want to kind of talk a bit about that because the next chapter in this tutorial, as part of the training, is to talk about cuDF. Right? This is the re-implementation of pandas that we have. It's the same deal as with CuPy, right? It's a different library that you import. It follows the same API as a library that you know. It has GPU implementation. You can go and write cuDF code, and that's great. But we also have the cuDF pandas plugin. And there's like a separate notebook that's not part of this course. If I just go back to AI, this is our landing page for stuff. But if you go to cuDF pandas, which is linked from here, pandas accelerator mode for cuDF, and then on this page somewhere there's this try out cuDF pandas. There's like a long-term Colab button, and I can just go. I'm going to grab a quick GPU from Colab so we can do this notebook while my other notebook's waking up. If you also want to like experiment more with this stuff, Colab's a great place to go and try out. You can get some free GPU resource. It does time out after some arbitrary amount of time. I think it's just based on demand of who's using it. So it's kind of, we used to run this tutorial with Colab, but it was always a bit, you don't know whether we're going to get to the end of the time with this time. But if you want to go play with this, you can do more things. But this notebook just linked from our website, and this talks about the accelerator mode in pandas. So let's go through that one. Let's run that piece. This notebook just does a video SMI just to show, okay, we're on Colab, it's given us a T4, we have GPU, we have CUDA, whatever. I'm going to download a data set. This is from the New York City's got some great open data sets. One of them is this parking violations data set. It's just got a bunch of lists of who got a ticket for what, where at some point in the past. So we're going to go and pull that down. It's a reasonable sized data set. It's like 0.5 gig. So it's not the biggest thing in the world, but it's also big enough that if you use pandas with this, you might feel some sluggishness, some pain around working with a data set of that size. Now, if we write some pandas code, we're going to open up this Parquet file, and let's just have a look at some of the data in it. Just normal pandas, right? Read the file, have a look. So you can see what state the vehicle was registered in, what kind of violation there was, what kind of vehicle it was, whether it was a van, or a car, or a pickup truck, or kind of, and the date and the ID number. And then we can do things like pandas operations. Right? I want to work out which violation is the most commonly committed by vehicles from different states. I want to do a group by, basically, of the violations by state, and I want to do a sort and a pandas list. Right? I wanted to manipulate a data frame, and I'm going to do this in pandas. And there's normal API. You have your data frame, you chain together all these different functions, and it does some computation to give you a result, and gives you an answer. And it takes a little while with a data set this size. We can run another operation, which is which vehicle body types are most frequently involved in parking violations, so working out which type of vehicle commits the most offenses. Again, this is a group by with an aggregation. We're going to group by a certain body type. We're going to call an operation. We're going to do a count. Maybe you want to do a mean. Maybe you want to do a max. Hopefully you can see how this maps through to the stuff we've already talked about earlier. Of we have these operations. They're quite parallelizable if I want to calculate these kind of things. If I want to do an aggregation, I can do that as like a reduction, like a tree. I can take the count of a subset of the data and then take the intermediate results, and I can add those together. And we can parallelize in a reduction way as well as a mapping way. I calculate these things. And then there's another example in here, which is just counting the number of days, by day of week. We're doing a group by day of week, and then working out what kind of, how many tickets do people get on different days of week. Standard, big science, bread and butter panda style. And you can see, more parking violations happen in the week than on the weekend. There's probably more people in the city than on the weekend, right? Now let's actually go through and time some of this. Let's see how long pandas takes. I should have cleared my outputs because some of the answers are stinking in here. But this first one where we grouped by the state, right? That took 7 seconds on this machine that it gave us to run normal pandas code on the CPU. If I do the there's vehicle body type group by, that takes like 1 second, it's a bit faster. And then this last one is the weekday group by node count, and that takes a few handful of seconds as well. There we go, 9 seconds. Right? So we've got stuff kind of in the order of 1 second to 10 seconds of computation time in pandas. Now let's do the same thing with cuDF pandas, as we're just gonna write our code. So that's the first thing I'm gonna do is just restart my notebook, just so that we haven't got anything or cheating with anything kind of cached in memory. This line of code is equivalent to clicking the little restart thing, but it's just so I can tab through. Now, we're gonna do exactly the same code, but before I run this code, I'm just gonna say load extension cuDF pandas. We have, Colab has cuDF installed by default in its default environment. You don't have to install any of these libraries or worry about any of this. You just load the cuDF pandas extension, and this is the like little thing that will intercept the pandas import, add a little proxy thing in there, and that proxy will handle dispatching to either try using cuDF and do things fast on the GPU, and if that fails for whatever reason, I'll then just go back to pandas, I'll do it with pandas. And I'll copy memory back and forth as we need to. So then we have the same code, right? Literally the same code. Pandas, import pandas as PD, I'm going to read my Parquet, I'm going to do my group by registration state. This cell is just copied from above. All I've done is load a different extension. But when I run this time, it took 2 seconds. Right? So it took 10 seconds when we ran on the GPU, it took 2 seconds. That was also the first time I did this, and there's probably some warm-up stuff in there. I think if I run it again, 750 milliseconds. I probably consistently run this 7 milliseconds, because that was just a little bit of overhead to, yeah, 760. Okay, so we've got this kind of 10x speed up on this operation just by loading a plugin. We're just in Colab, we haven't had to do much different at all. We can do the same with the group by body count. This one was 1 second, I think, wasn't it? So now we're down to 28 milliseconds. We can do the same with the weekday group by. So that was 8 seconds, something like that, 9 seconds, which are down to like less than half a second. So you don't have to change any code, you just keep using pandas, like pandas in the data science community, right? And so you just come in, you just add the GPU acceleration, and that's great. But it's also magic, and magic makes people a bit twitchy. It makes me twitchy sometimes. It's like, oh, I've got this cool plugin and it does a thing. I don't really know how it's doing the thing, and maybe it's doing things that are not the right thing, and maybe I want to understand. How do I understand, I guess, is the question. So there's all these tools built into the plugin as well to help you really look at and investigate what is going on. Yeah, so there's a note in here that just says Colab for me, but funny with these tools, but I don't know why that link's in there. But one thing we can do is we have this other magic, which is cudf.pandas.profile. And what this will do is it will run through all of our code as it would before, but every time it makes a call, it will show us at the end. We tried to call cuDF, it took this long, we did this, we did that, we did this, oh, this failed, we should fall back to pandas, we're gonna now run it, it took this long. So there's a little bit of code here. This is a very basic example, but it prints out this kind of table. So you can see, we constructed a data frame, it did it on the GPU. We called concat, it did it on the GPU. We called min twice, and it took this long each time. We called group by, we called get, and like you can see each function call that we did in the pandas API. And in every example in here, the GPU call was successful and it worked, there's no fallback. We used to, this example in an earlier version of the plugin, the min call would fall back to CPU. It was like not implemented setting the access to access equals 0. So that was like an example, I think it's still hanging about in this notebook, of like showing where it falls back. When it fails, now I guess that's just been implemented, so it didn't fail. That's nice too. But if that min had failed, if cuDF had raised an exception, like a not implemented error or something, the plugin would just catch that, copy the memory to the CPU, call the pandas equivalent, and move forward. And then it would go, okay, I'll try and do the next thing on the GPU, it does it for you. And it shows you. So you can see where your time's being spent, you can see where you're getting gains, and if it is not behaving as you would expect, you can get a breakdown of like, where is it failing? Maybe you see a situation where every single call for some reason falls back to the CPU. Maybe you have 64 gig of RAM in your machine, and you've got 16 gig of RAM in your GPU, and you're trying to work with a data set that's 40 gig or something, like every call is going to fail because you'll run out of memory on the GPU every time. Right, so we'll just fall back to the CPU, and that will chug its way through. It's probably a little bit overhead, let's try and each different one. But this will show you. This will show you the breakdown of where things are failing, and you can dig into the errors and understand what's going on. It also has line profile. So this is the first one is profile. This is line profile, and this one prints out your code line by line and shows you. Doesn't work. Dot jump in. Okay. Yeah, this one shows you line by line. I record this line and took this long, record this line and took this long. Yeah, it's kind of what I was talking about. Maybe that one did fall back here. Yeah, we called min on the data frame. It tried the GPU failed, so then it tried the CPU, and the CPU succeeded, and then it moved on and did the next thing, and it did the next thing back on the GPU. So this is all great for debugging and understanding what's going on. Now the rest of this notebook goes on more into depth of like how the magic import intercepting stuff happens, and if you're like really into Python developers and will understand how that's done, I would encourage you to go read the rest of the notebook, but I'm not going to dive into exactly that. But just to say, we have this zero code change thing. I should be able to get Jupyter back again, so we can carry on with the rest. But that's just to show you this is kind of the direction we're going. We have all these libraries, these libraries like Numba and CuPy and things to help us build out code. But equally, your first starting point is just use pandas. Go and use the plugin. One of our more recent announcements is Polars, right? Polars has native GPU support in it. Now you could just go and use the GPU. That's not like a plugin in the same way. You like set it in Polars. But like if you like Polars and want to use Polars, great, go and use Polars. Like it's got GPU acceleration built in. You only need to dig deeper when you start hitting the performance limits of the zero code change star. Right? I want to I've turned on the plugin, I've got some speed up. I actually want to see if I can get more speed up out of this. I'm going to dig deeper. I'm going to move down into where I want to land. So hopefully that's useful. Now this notebook kind of is similar to the CuPy one in that this notebook walks through the API of cuDF, and the goal here is to just demonstrate to you that it's the same API as pandas, and you can do all pandas in Linux. So we can run through this probably reasonably quickly. I can import cuDF, I can import pandas. Pandas has a read CSV, cuDF has a read CSV. You get the idea, right? Like that, I don't necessarily know if it's worth writing through all of this. If you want to use cuDF directly, there are interesting things you can do with cuDF. Actually, I will write down a bit further. There are things that you can do. Hi. Let me just run these up. These are they're showing you pandas things. One thing we talked about actually in the Numba section that is interesting is some people ran into some string issues. We did the fizz-buzz stuff. If you try and assign the string into the NumPy array, you get type errors, and GPUs are traditionally not known as working well with strings, but pandas is like all about strings, and there's loads of string stuff in pandas, and it's very common to want to work and manipulate string data. And so in order to make cuDF, we also built out a library called cuStrings, and there's like this whole implementation for handling string data on the GPU that you don't really need to worry about the implementation of, but you can just do your normal pandas operation. So if you want to do, this data set is like Wikipedia pages or something. So if I want to take the title of every page and uppercase it, we can accelerate that on the GPU, and it uses cuDF strings to accelerate just uppercasing a string. That's a very parallelizable operation as well. You just use the pandas API to interface with that. Means the word. So there are no kind of string limitations up here. I think there is a limit on how many characters you can have in a whole data frame. The number of you top. Yeah, there's like a limit, isn't there, like how big your string data can be.
So you could have a maximum of 2 billion rows.
2 billion.
But your strings can be arbitrarily long.
Okay, cool. Okay, yes, there is some upper limit.
Yeah. And you can work around that with Dask to have even larger data sets if you have more than 2 billion rows.
Yeah, exactly. So we'll come on to Dask if you've got time. There's on the section. But one thing I do want to show you from this notebook is one thing you might get onto in Pandas world or some NumPy world or other things is user-defined function, right? Some function that you want to apply to your data frame, to your array. And cuDF has got a bunch of machinery in it so that you can write normal UDFs, right? Some kind of function like this where I'm going to take in a value, and if the value is less than 5, then I'm going to return 0, otherwise I'm going to return the value. There's just some kind of logic that you might not be able to express neatly in a Pandas call and say, like, I'll write a function and I will do apply on my data frame so that I go through every value and do this. And one of the nice things about cuDF is it will handle converting this into a CUDA kernel, use Numba to compile it down into something that can run inside grids and blocks and magic and whatever, and then it will run that against the cuDF data frame. So you can basically write normal UDFs and apply them against a data frame, and it will happen in parallel. We'll do this operation in parallel. You have to write a Numba kernel without worrying about Numba at all, like it's doing the Numba piece for you. But you can also, if you do want to write a kernel, like if I just assign this one, we can do from Numba import CUDA. We can write a kernel just like we did earlier. We're now going to say, okay, I've got this kernel. The way that the API of this works is it assumes that it's going to pass you an array that represents the input, the column that you're operating on. And it's going to give you an empty array of the same shape for you to put your output into, same way we were doing with Numba before. And it will also pass in like other arguments if you want them. It follows the like for all API in Pandas. No, it's the for all API in Numba. And you do the same kind of thing, like I say, which row am I, get the index, and if I'm within bounds, you do your normal kernel writing stuff, and then you can do my kernel.forAll, and then pass it the columns from the data frame. So this is a slightly different way of doing this API. We're not calling it the kernel, passing it as the data. We're we're doing more of a map type operation. This is kind of getting a bit deeper to this. I'd encourage you to look further into the documentation if there's interested. But cuDF supports writing these kernels. So if you want to start at the Pandas level, do the zero code change stuff, and then maybe you're like, oh, actually, I can imagine how I would write a CUDA kernel to do the thing that I want to do on this column. I'm going to go down into cuDF and change my import. I'm going to change a little bit of code. Then I'm going to write a kernel and apply to that. And you're starting to slide down that stack into having more and more nuanced code. And there's a little example in here that shows about doing like rolling windows as well. So we'll be able to apply a kernel loop or rolling window. Yeah, go on.
Yeah, so it's like we're talking about stack operations, CLX cuDF. It's transferring memory to the CPU, so we haven't seen state direct number operations, but what we get back is.
Yeah, so the question is when we're working with string data in cuDF, like what are we transferring to the GPU? Like cuStrings is kind of wrapping all of that up for you. So like in Python mode, you have a string, it moves to the GPU, you do operations on it, you bring it back to the CPU, it's a string. Yeah. You don't need to worry too much about the need to be representation is on that. On the GPU, it just has all the operations you would expect it to have, but like restricted accounts. Cool. Okay, that's the end of the cuDF chapter. So if you've got any more questions about any of this kind of data frame related stuff in Mac, yeah, go for it.
Can you do the write in the cuDF with the link to the computer, like that we want to?
What can cuDF write into the GPU memory? Is that the question? Yeah, so cuDF has all the same functions like read CSV, read Parquet, whatever, and it will read into the GPU memory directly in the same way that CuPy will if you create an array into there. And these are those situations where like the CSV reader in cuDF is really fast because there's some compute that needs to be done as part of that. cuDF handles that for you. Again, with the plugin, you just the plugin when you do pandas.read CSV, you get the fast implementation, right? Go for it.
Is this compatible with Apache Spark?
Is this compatible with Apache Spark? Yeah. Yes and no. There's
there's a separate product called Spark Rapids.
Yes, exactly. So this stuff is like a separate some of the stuff we've shown here is how do I take pandas and add cuDF to it. But cuDF is a Python library, and underneath that, there is a C++ CUDA library for libcuDF, and that's reused in other places as well as building out the cuDF library. So there's a project called Spark Rapids, which adds the kind of cuDF lower level implementation into Spark, So you can write Spark SQL, you can do PySpark, you work through the Spark API, and Spark handles actually calling like our GPU implementation of the data frame operation rather than its own native ones. So when you start the Spark cluster, you load a plugins. And again, it's another one of our kind of like, this is zero code change too. You just load a plugin into Spark, you do normal Spark, you get GPU acceleration. There's loads of documentation for Databricks and Riehl and whatever platform you use for Spark in the PySpark docs. Same with the Polars one as well, right? It uses the same underlying library, but like just wires it up in a different way into a different library.
So just can you also provide the functionality to be able to use that cover of threads beside their
Okay, the question is, does cuDF ask you to provide threads and blocks and grids and I don't know, that kind of stuff? So the goal here is to abstract all that away from it. Like it should make sensible decisions about how to tune things up. Does it let you tune those things if you want to? No. No. Okay, no. It does those things on your behalf, so you don't have to worry about this is part of the goal of the tutorial. We dive deep to give you like a fundamental understanding, and now we're back up to that. We don't really need to worry about that anymore. It's all okay. So, okay. Any more data frame questions? Yes.
If the data frame is larger than the memory itself of the GPU, then does it do bashing automatically, or do we have to handle that?
So this is where we get onto other libraries, right? Like if you fill the memory, you fill the memory, you get out of memory errors, like it won't do any kind of batching. It's the same as using pandas on the CPU, right? If you try and open a CSV that's bigger than your RAM, pandas will give you an out of memory error, right? cuDF will do the same thing, and it's good to be like aware of, okay, I have this much RAM in my machine and my GPU has this much memory. Maybe they're the same, maybe they're different. I need to think about my data set. So this is where we sometimes get the fallback in the plugin, like, oh, the memory on the GPU is smaller, and so I'm still thinking in, oh, this worked in pandas, right? Because I've got enough RAM, but now when I try and run the GPU one, it doesn't work. And so, oh, it's because you have got less RAM.
Well, could I add to that?
Please do.
There's also, in cuDF Windows specifically, we enabled a feature called managed memory. So you can exceed the amount of memory that's on your APU, and it will spill some of that to CPU. This allows you to get around some of the out-of-memory errors you might otherwise encounter. There are other strategies for this, and I'd be happy to talk with you more. Absolutely. Thank you, Count.
Okay. Any more data frame? Cool. Okay. We've had a couple of questions about multiple GPUs, larger than memory stuff. I'm aware we've got like 25 minutes or 20 minutes left of the session. 50. How long have we got that?
15.
Yeah, like 50. Okay, we've got 15 minutes left of the session. There's 2 notebooks left in the tutorial. One is cuML, which is machine learning, scikit-learn type stuff on the GPUs. The other one is Dask, which is multi-GPU, distributed. I want to work on stuff that's larger than memory. We probably have time to like go through one of those very quickly. So who would prefer to go through the scikit-learn machine learning type stuff? Hands up. Who would prefer to go through the Dask distributed out of LA stuff? Hands up in the comments. Maybe Dask. What do you think?
It goes that.
Yeah, okay. That's good because I work a lot on Dask and probably much better to talk about that than other people. Okay. So if you've not come across Dask before, Dask is a Python library for distributing Python computation. It can do low-level task scheduling, like say I've got a function and I want to do maps and that kind of thing. It will handle calling different functions at different places. It creates a graph. It does kind of lazy computation of things. You can set up a chain of computations, and Dask will build up a graph of what you want to do. And then when you actually try and read a value or do something tangible, it will go and execute that graph in kind of the board. It's similar to Spark in some ways. It's similar to Riehl in some ways. The different projects all kind of fit in the same kind of space of big distributed. I want to do larger than memory work or to do multi-machine work. And we use Dask a lot in Rapids to do multi-GPU workloads. So say I have a data frame that is 10 terabytes and I want to do some operation on that. I can fit that into memory, whether I'm using pandas or whether I'm using cuDF or any of the plugins. Like I just can't load that much memory. I need to load it in batches and work on it in batches. So Dask, although Dask has this low-level implementation, it also has these high-level collections. One of them is called Dask Data Frame, which is, again, it's one of those things that it mimics the pandas API. It lets you do larger than memory operations on tabular data in the same way you would with pandas. And it just loads in chunks of memory as individual pandas data frames and then does operations and then handles. It has algorithms for stitching together. So if you want to do a mean or something, it will do a tree reduction mean and that kind of thing. We also have like Dask Array and Dask Allen and all these other libraries in there. But one of the nice things is that because Dask data frame uses pandas data frames as its chunks, we can just pull out pandas and put in cuDF instead, right? It follows the same API, behaves the same way. So we can do distributed GPU data frame workloads with Dask in the same way we do a CPU. Now, I'm sure myself exactly where this lever goes. Yeah, fine. Okay, so one of the things you have to do with Dask is you create this client, this object that connects you to a Dask cluster. And when you import Dask and just use a client with no configuration or nothing useful in there, it goes, okay, I'm a single machine Dask cluster. I'm just going to have how many CPU cores have you got? How many, what have you got? What resource can I use here? And it creates this little cluster object for me automatically. And it's decided that this VM has got 4 cores and it's got 16 gig of RAM. Dask has kind of coded that for doing some work. And then I could do something like I can submit a function and use it like Futures API style thing and say, go and run my function for me. Or I can do a high level collection. So here's like a NumPy type thing. I can say, make me a random array, chunk it up into NumPy arrays of this size, and then calculate a mean. And the compute tells it to do the latest thing. And Dask will kind of break this up into this graph of like, okay, I'm going to build this array in all these chunks. I'm going to do a mean of each one, and then I'm going to bring those intermediate results together and take a mean of those. And it handles doing all of that for you. And so, yeah, okay. When you want to run these things, the basic way to do it is with a local cluster like that. You just let it grab the machine that you're on. But if you want to do distributed computing, you probably have servers somewhere that you want to use. You have cloud platforms somewhere. Maybe you have Kubernetes. Maybe you have access to an HPC. And you have Slurm sort of submit jobs. Or you're on Spark and you still use Yarn or something. And you want to submit some kind of multi-node job to that. We have all these Python packages that let you launch Dask clusters on various compute platforms. One of them has to be the scheduler. The rest of them are workers. They all talk to each other. You connect your client, and it kind of sends the Python code over to them. They do the computation. And they're all kind of managed through these classes here. Now, one of the ways that I used to work in weather and climate research, and my colleagues all used to use Dask we all had desktops, right? We worked in a big office, we had desktop workstations. And people would SSH into each other's workstations and turn them all into like a Dask desktop, right? So you would kind of siphon your colleagues' CPU time to build out these big clusters. This was like my entry into Dask. And then we started running HPC and cloud and whatever. So you can do SSH cluster, and Dask will just like bootstrap on a bunch of machines that you could SSH into to run its workloads. But then when it comes to doing GPU stuff, we don't want the Dask cluster to come up and say, how many CPU cores have you got? How many memory have you got? We want it to say, how many GPUs have you got? How much GPU memory do you have? So we have this package called Dask CUDA, which has like another implementation of the local cluster. When you create this one, it just has a look at the machine and says, how many GPUs do you have? In this case, it will find this one A10G that's in here. And I can connect a client to that cluster. And then I can do things like I can submit, I can write a CUDA kernel, and I can submit that CUDA kernel to Dask. And this is nice in a way where like, my laptop doesn't need to have a GPU now. I have some machine somewhere else with a GPU, and then I'm going to use Dask to submit functions to execute. That's the low-level representation. But I could also use Dask cuDF, which is this implementation of Dask data frame, pandas type stuff that uses cuDF. And so this reading needs updating actually, this was on the best one. But if I want to load a Dask data frame that's made up of many cuDF data frames, I could do that, right? And all of this is lazy, so Dask's quite nice in that if you look at a data frame before you've done any computation, it's read at least the metadata out of the file and kind of like, okay, I know what my columns are called, I know I've probably got some number of rows, I've broken this up into a certain number of tasks or a certain number of expressions. But then if I actually do some compute, if I call head on this, it goes, okay, I need to actually read the first chunk, the first file to at least get the head out of it. and then I can return that to you. Or if I do like a length, it will read everything and do the actual computation. But this Dask is kind of breaking this up into this big graph of all these small data frame operations, and we can accelerate those with GPUs. You kind of get this, you're kind of scaling up by adding accelerated hardware, making the individual operations go faster with the GPU, and you're scaling out onto many GPUs, many machines, so that you can work on larger data sets or things that you wouldn't be able to process on a single machine. And you do the standard, I can do a pandas group by and calculate the mean in Dask that's going to use the GPU. Normally I have a white dashboard showing you what's going on, but the dot is broken, so I apologize for that. But there was that notebook, wasn't there, actually, which shows this one. This GIF that I showed before actually is from a Dask operation. So at the bottom you can see the Dask tasks running along on the hardware that we have. This progress bar is showing we're chugging through all of these different cuDF operations, and each row in this kind of task stream is one GPU. And so you can see these tasks being executed on each GPU. That's making GPU utilization kind of click on it. So Dask is great for doing multi-GPU stuff. We also can make use of accelerated networking in Dask. So by default, Dask uses TCP to communicate between the workers. But if you're on NVIDIA hardware, maybe you've got a server with 8 GPUs in, they're probably connected together by NVLink or some kind of shared backbone. Maybe there's multiple servers in a machine, and they've got like at least NVIDIA Mellanox switch with InfiniBand, like these more accelerated networking technologies that you might find in HPC centers or on cloud platforms with the bigger instances. There's a technology called UCX, which is like a high-level networking library, which works out the most optimal way. It looks at your hardware and it goes like, oh, I want to talk from here to here. I can use TCP, but actually there's an InfiniBand, so I'm going to use that. Well, actually there's NVLink between these two GPUs. I'm going to use that. Like upgrades you through faster and faster communication to reduce that latency of things having to talk to each other. So UCX is kind of another project that we work on a lot to make sure that Dask, the GPUs in your Dask cluster, can talk to each other as efficiently as possible. Okay, that's probably it. We don't have time for the QML notebook, but if you are interested in that, I encourage you to go through. I think I've been talking to you for hours and hours at this point. I hope this has been a useful session for you. Like, we've covered a whole bunch of different topics here. The high-level takeaway of this is that we're trying really hard to make it so that you can just go and use these technologies without having to rewrite all of your code. You can just go and try stuff out, see if you get some acceleration. People have like great results of just dropping plugins in and seeing how fast things will go. But as you want to like move deeper, and you can tune things and learn new libraries and move further and further down that stack. And like the Python layer exists in a whole bunch of libraries, and they hit the C++ border, and then you can move even further down to write really, really hand-tuned codes. But you can start right at that top, and there's like nice, easy on-ramps to get going with these stations. So thank you all for sticking around to stay with this. Does anybody have any other questions or anything you want to add broadly about any of the things we talked about today? Go for it.
So we see Python was that's about using Python, doing decent Python or C++. Do you see any problems before?
Do I see anyone using Python or C++?
Yeah. Do you see any performance difference? Do you see difference in any performance here?
I mean, I think a lot of it is about what you know as a skill, right? Like this is PyData, like people here know Python. Like you don't have to go and learn C++ anymore in order to be able to leverage this hardware. You can go and get started with Python. And like we had that slide in the open deck kind of shows that we call it like the swim lane, right? But like each level here, you've got zero code change Python at the top, and you've got low level C++ code at the bottom. And like as you move down this stack, you can squeeze more and more performance out. You can learn more, you can do kind of more intricate things, and you can squeeze out a bit more performance, a bit more performance. But it's up to you, like what your requirement is, what do you need? Like if going and just using the top level, like I'm going to get 10x to direct speed up out of pandas, and that will benefit me, go and do that. Like, and you can work entirely in the Python space. But if you're like, oh, I want more performance, I want more things, you can move further down. Of course, you need different skills and different things, but you can if it's valid to you.
Great one. The examples that you've shown, is there a GitHub as well for that?
Yes, there is. So if you go and search NVIDIA Accelerated Computing Hub, should be linked in the thing, but this repo here, Video Accelerated Computing Hub, has a GPU Python tutorial. This is all of those notebooks that we've gone through today. They're on GitHub, they're under license. Go try to swim, but no, cool.
It's like it. For real, please give that repo a start.
Yes, please do. Of course. Yep, go for it. Do you want the microphone?
Yeah, we want to help contribute to cuDF or cuPy. How do we do that? What is it like communities?
Yeah, absolutely. So if you go to github.com/rapidsai, oh, expect the SSO, sorry. Okay. All these repos are GitHub repos. They're all openly licensed. You can go find them on GitHub. There's a whole bunch of issues and, this is a whole community. So if you want to come and work on these things or learn about these things, please do comment on issues, talk to us. I think if you go to rapids.ai, there are also links to, I read that. There's links to like all of our community stuff at the bottom. You can go to our Slack, Stack Overflow, just, there's lots of ways to like get in touch and get engaged in the community. But all of these things that we've touched on today are open source, GitHub hosted project.
Do you know if any of this is available from like AWS serverless resources such as Google or Lambda, something like that?
Okay.
And
The clouds have different levels of like managed GPUs. Like I think if you go right up to the Lambda level, you won't find like this kind of stuff. If you come down to like Fargate or like managed containers or something, some of those have GPU offerings. If you use any of the like managed Spark platforms or things, there's lots of places where you can like add GPUs in those levels, but like it's like a lot of these libraries are quite large in size, and that's one of the bigger challenges we find with serverless. But also you want to be doing a reasonably sized computation. And so, the way that people typically build things with serverless is you're going to be invoking this function many, many, many times. So lots of users from distributed places, and each core is probably pretty small. So like, it might not be the best fit for GPU stuff. Whereas if you kind of come down a little bit to like, you don't have to manage VMs, but like you can manage services that have GPUs being there.
We also have deployment notes.
We do. If you go to Rapids, if you go to the Rapids documentation and go on deployment guidelines, there's like a whole section of like, I use this cloud, I go on here, I use this service or that service on whatever cloud platform, and it talks you through installing the libraries, getting containers, getting set up, making sure drivers are working. And there's also a whole workflow example section. So this is kind of opinionated notebooks on. We've spoken to somebody who said, we use this AWS service and we do this thing, and I'm trying to solve this problem and I want to use this library. And we put together kind of like a best practice notebook on that problem in that configuration, in the hope that, if you look at this and you don't see your preferences and tools and workflows represented, just open an issue and tell us, and we can kind of, we want to make this a useful resource to show you kind of common pathways that you might take in using these libraries of cloud.
Last question.
Last question.
For folks continuing to work through the tutorial, are you around for the rest of the day and week?
Yes. So a bunch of us from NVIDIA will be around through the rest of the conference. So you should still have access to this material through DLI. I think you have access to the material for
3 months.
3 months.
Yeah.
So feel free to work through the notebooks. Obviously the notebooks are on GitHub, but like this platform will give you access to run them. If you have any more questions, come and find any of us. I'm more than happy to chat further about it.
Thank you, everyone.